with that, just let us know. And I guess we'll manage that. It shouldn't be a problem. Recording started. Okay, then we can start. Yesterday, we covered the introduction to supercomputing, how to log into the system. We went through the 5 systems available, the limits we have on the 5 systems, and how to properly use them. And we illustrated what software is available on Cetonix, and we can install yours or use containers to run your workflows. Today, we start with the second part of the training, looking at the accounting model. There's someone running just in time.
Yep.
We are starting today with an overview of the accounting model, that is how we charge for jobs on Cetonix. Deva then will follow. Session. Okay. Then Deva will follow with a presentation regarding running jobs on Cetonix. So you can write your job script to run your workflows on Cetonix. And we end with an overview on how you can use Acacia to store and retrieve your data. In this particular presentation about the accounting model, the goal is to illustrate, to describe what is an accounting model and how it is used to define computer locations. What is a computer location? Now it's used to assign time on the supercomputers for research projects. We will go over the accounting model we implemented at Pawsey, so how we came up with it, what is it, and how we came up with it, and why it charges jobs the way it does. And we end with a few tips on how you can monitor your computer location and how you can monitor the consumption of the service units. Again, we have a few symbols throughout the slides, identifying new concepts, best practices, warnings, etc. Pay attention to that, and we also have links to documentation where these topics are discussed more in detail. All right, we start saying that supercomputers are a shared resource. It's a shared resource and a shared infrastructure. They have a very large computational capacity, but it is finite, right? And not only that, the supercomputers are very expensive, and they are replaced every 5 years or so. And they consume electricity, whether they are running a computational job or not. So the goal is to keep them as busy as possible throughout the years. This includes also nights and weekends. So we want the supercomputer to ideally run computational jobs as long as possible, as much as possible, maximizing the usage. Now, the way we achieve that is through a combination of few things. The accounting model defines, first of all, we need to define what are the resources that are being given to researchers and how much of those resources are available throughout the years, and then how we quantify the consumption of those. And then we distribute, when we define such thing with an accounting model, we quantify how many of those resources we have throughout the years, and then we distribute them across researchers using computer locations. The scheduler, in our case, SLARM on Cetonix, will take care of taking researchers' jobs, requests to run applications, and schedule them on the system throughout the time such that the usage of the system is maximized. Well, it has a few KPIs to maximize. So, of course, we want the jobs to run as quickly as possible, but also we want to allocate the jobs such that the system is utilized at its best. So an accounting model is essentially a it's a mathematical model describing what resources are available and what what is the cost of that resource, of using that resource. And that cost is expressed in the service unit, which is related to the definition of accounting model, let's say. And the unit, but the service unit, you can see, are the unit of measure for consumable compute resources. Now, while we say consumable compute resources, yeah, the CPU is, it's always there. Let's say it's there, but the problem is the consumable resources, the hourly usage, the usage of that resource in time, because while the CPU, let's say CPU core, is always there, you cannot, if that goes utilized for 1 hour, that hour is lost, and we have a finite amount of hours throughout the years. So we want to make sure that the resource is used at every time, as much as possible, ideally at all times. So the consumable resource is not only the CPU, but we call it the CPU hour. So the 1 hour use of that CPU. And that is something, you have a finite amount of CPUs, a finite amount of hours throughout the years, and so you have a finite amount of CPU hours available throughout the years on the system. Traditionally, we have the service unit, that is the consumable part of a supercomputer, was the 1 hour use of a single CPU core on the supercomputer. This has always been the definition of one service unit. So the accounting model usually was as simple as saying 1 hour use of a single CPU core is equal to one service unit. And then you would compute the cost of your jobs based on that accounting model. But as we go into modern supercomputing, we have an infrastructure that is rather far more complex than the previous years. One big difference, evident difference, is that you have a heterogeneous system. We have GPUs available on the system, and so how do we charge GPUs? Do we charge them the same as CPUs or not? So there was some thinking about how can we charge a GPU? What is the reason? What is the rationale behind the number we came up with? So on Cetonix, we have we retain the definition of service unit for the CPU. So we have one service unit is equal to 1 hour use of one CPU core. But then we say that 1 hour use of one of the two GCDs of one AMD GPUs, or put it simply, 1 hour use of one virtual GPU, let's say, the one you can see on SLAM, one GCD is equal to 64 service units. I will explain why we came out with that number in a moment. However, based on having that definition, that is a first start, but it's not the whole story. But having that definition, the cost of a job on Cetonix depends whether you are on a CPU, on the CPU partition or the GPU partition. On the CPU partition, the cost of the job is the number of CPU cores you're using, multiplied by the work time, and that will give you the cost. Or if you're in a GPU partition, it's the number of logical GPUs or GCDs multiplied by 64 and the work time. You can similarly, based on that formula, you can compute the total cost available, the total amount of service unit available on Cetonix throughout the year, and that is used then to partition, used as a base to partition the service unit on the throughout to the various allocation requests. We have a few examples here. For instance, one service unit is equal to 1 hour use of one CPU core or half an hour use of two CPU cores. 512 service unit is equal, can be the charge of 4 hours, can be the cost associated with 4 hours use of one MI250X, so two GCDs, or can be 4 hours, so one Setonic CPU node. So what we see is like one of MI250X, the 1 hour use of one MI250X is equal as 1 hour use of Acetonics CPU node, an entire CPU node. Now,
So this is
yeah,
just quite an interesting definition.
yes.
So is it something specific just for Setonics, or is it like some sort of a standard that?
So the reason we have, I will come back to that later. I don't want to. I will explain why we came up with that number, and the reason is basically it's defined based on the energy consumptions of the machine. So I will discuss a bit later. I want to go through. I will open. Actually, we brought a paper about it, and we'll open the paper. And if we have time at the end, I will go through.
Sure.
Okay. Another important thing to know is that it's the counting model is slightly more complicated than that, in the sense that the first thing we thought about is that, okay, so far we only taken in consideration resources such as CPU cores or GPU, so the resources that do the computation. But what about memory, right? Because you can use one single CPU core on a node, but then use the whole memory, and then in practice the other cores are unusable for other people.
Yes.
Right.
Yeah.
So this was not taken into account in previous accounting models in Magnus or Galaxy, also another center. So what Maciej and I thought is that memory is important as well. So what we say is that what the actual definition of the accounting model is, what we charge is we consider the CPUs and the memory. We look at the largest fraction between the two of the two resources that have been used. For instance, in this case, let's say you're using 3 cores out of 6, but then you're using 4/6 or like 2/3 of the RAM. Then what should you charge the user for? So what we say is that, well, it seems reasonable to charge for the RAM consumption rather than for the CPU consumption, because effectively you are taking the fraction of the RAM associated with the fourth core.
Yeah.
So what we do, we allow share resource of a node. So we allow different jobs to share the same node, but then we need to charge each job for the fraction of the node it's using, and that fraction is the largest fraction across all the fractional use of all the resources. It means that if we take into consideration the RAM usage and CPU usage, which one is the largest fraction, and we take that.
Yeah. So even if you are using less memory and more cores, you will just charge for that fraction of the node.
Yeah. Okay. So what we do is the way it is implemented in practice is that when you ask for a number of cores, you are only given a certain amount of memory that is associated with that number of cores.
Yeah.
If you need more memory, you need to ask more cores, even if you're not using it. So in this case, we pin the memory usage to the core usage.
Yes. Okay, that brings quite a bit of clarity.
Okay. And once we pin the memory usage to the CPU usage, then the accounting model can say CPU core hours, but that core hours is actually associated with the memory as well. Also, just as a reminder, if the job finishes, when you specify the job script, the batch script at work time, if the job ends before that, then you're only charged for the actual time the job ran, not the work time expressed in the job scripts.
Yeah.
Any questions so far?
I've got a quick one. So the wall time multiplier is the one. Is that the one which will is going to inflate the number for many of us?
The work time,
Because in all your previous slide, in the formula, there was that multiplication by wall time.
so yes, it's the work time is an unfortunate error. I think it should have been
Execution time. How long does the job run for? Like even though it requires for 24 hours, if the job run for 2 hours,
Yes.
you'll be charged for only for 2 hours.
That's my question.
Yeah, I think-
So let us say I have a CPU efficient job,
Yes.
but let's say for various IO related issues, or whether I'm using like a scratch or issue, scratch related issues, or even like a MPI overheads or something.
Yeah.
So when that wall time goes higher
Yeah.
for performance, IO performance issues, so that will basically inflate the actual cost of processing.
Yes.
Right?
Yes.
Right. All right, that's an interesting thing we have to deal with.
So probably that wall time should be replaced with elapsed time.
Yes.
Something, I think, based on the experience that we are going through and issues we have been having, particularly, that with IO performance on both Caravan and Cetronics, and the fact that, particularly the certain applications like a beamformer, as it's like IO heavy. Right? That will change.
Yeah. Okay. Now, okay, this was another example. In this other example, we have these two examples. The first one is the one I illustrated before, where we use more RAM than number of cores. And this other example, we're using more core than RAM, more cores than RAM, but the end recharge is what you're charged at the end is the same, because you're always using 2/3 of the node.
Yeah.
So for GPU nodes, we have the following. We have 8 GCDs or virtual GPUs per node, and we have 64 CPU cores. And then we have also the memory. So on CPU nodes, we had the CPU cores and the memory. In this case, we have the GPU. In addition, we have the GPUs as well. So we have these 3 categories, and the same reasoning applies. So the largest fraction of resource you use is what you're charged for. Okay, so if you're using 1 GPU, but then you end up using all the memory, then you're charged for 8 GPUs.
Okay.
And similarly for the CPU cores. Now, similarly, what we do, we pin the 2 resources to a third one. So the main resource is the GPU, because you're on a GPU partition. We want you to use the GPUs. So when you submit a job to the GPU partition, all you have to do to specify is how many GPUs do you need, how many GCDs, I would say, but virtual GPUs. So I'd say you request only 1 GPU, then you will be given 1/8 of the cores, so 8 cores, and 1/8 of the memory available.
Okay.
So if you need just 1 GPU, but then you find yourself you need more CPU cores or more CPU memory, then you would need to request more GPUs. If you try to request a number of cores explicitly on the partition, it would start complaint says you can only request GPUs. Then the rest of resources is given proportional to what you requested, to the number of GPUs requested. So let's see if we have. So the minimum cost to use GPUs is 64 service unit per hour. That was the cost of a single GCD, and the whole node multiplied by 8, you have 512 service unit per hour per GPU node. Okay. So here are a few examples of that. Few examples of the charges here. So we have running one for 1 day on 8 CPU nodes would cost you around 24,000, 25,000 service units. So it's 24 hours by 8 nodes by 128 service units, because should be like there is 1 service unit per one core. And so you have 128 cores, and so it's going to be 24, so around 25,000 service unit. Yeah. So let's say running for 6 hours on 4 cores within a node, requesting 115 gigabytes of RAM, that is half of the memory. So you say, well, 4 over 128 is this fraction, but then you have half of the memory, so you actually charge 6 hours by half of the memory, 0.5.
Yeah.
Plus 128, which is the would be the total number of CPUs, but half of you're charged for half of the CPUs because you're using half of the memory.
Right.
And that would cost you 388, 86, 84 service units. Any questions so far? Okay, seems everything's clear.
There are two numbers basically. One is the service units, other is the cost.
It's so the service unit is what you're going to be charged for. So it's the cost of the job.
Yeah.
It's the cost of the job. So I use service unit or cost. The cost is expressed in service unit.
Yeah, on Magnus and Galaxy, we used to call as core hours.
Yeah, that's what traditionally
we can core hours. Yeah, because we cannot call it core hours anymore because we are charging for GPU.
Sure.
And more examples here. So a computer location is basically an amount of service unit awarded to a project that was successful in a merit allocation call. When you get a computer location on Cetonix, you get a certain amount of service unit per 1 year or even multi-year allocations, but let's consider 1 year allocation. Thus, that allocation is evenly divided across quarters to encourage usage of the resource throughout the year, because we don't want researchers to think, oh, I'll do everything at the last minute, at the last quarter.
Yeah.
But then something happens and you end up not using the whole thing.
Yeah.
So it's good, again, to maximize the use of the supercomputer.
Yeah.
And the service units are allocated based on merits and the very share of usage of the resource. And what else? We have the Pawsey account balance tool to see what's left of your allocation. So you can control the usage of your allocation through this command line tool provided on Cetonix Pawsey account balance, which also was present on Garavarla. Okay, this is an example. Now there is this difference or this difference. The way the allocation works on Cetonix is that you will have, if you ask for CPU time, you will ask for CPU time and GPU time separately in the same proposal, but they are accounted separately. So you have the way it is implemented in SLAM is that you will have a allocation for the CPU, and then you will have an allocation for the GPU partition. So the service unit, the model is unified, but then you have two different allocations, and you will be charged service units on different projects. So you will have, for instance, in this case, the Pawsey 001 is the Pawsey staff project. So this one shows the usage of the CPU partition. So the allocation for the CPU. There is a corresponding allocation for the GPU partition, which is essentially the same project code, but there is a suffix -GPU to identify the GPU allocation. That is more of an implementation detail. But it's the same project, you have same directories, everything, but on the allocation, just for allocation matters, you will have two projects code. You will have your project code, in this case, for instance, Pawsey 001, and then you have Pawsey 001-GPU.
Okay.
And Yeah, then you can also see the usage of the consumption per user. So it's very important to monitor users, and it's the PI responsibility to make sure that users have the responsible use of service units, because if they finish, it's for the quarter, it's finished, and you have to wait.
Yeah, I think a couple of days back there was a ticket where the PI was asking, can I limit the user? Like, one of the user is dominating the entire allocation. So can we limit? There is no such mechanism. So it's the PI's responsibility.
Sure. All right. That's understandable.
Okay, so this is the end of this, but I wanted to share to open. Let me see.
That's the other cultural change we have to bring in, because up until now we have been mostly like watching that storage. This is the thing, but this is like the other important thing.
Yes,
particularly the way things are accounted.
right. So we brought a paper on how do we define the accounting model here. And a few years back.
Okay.
And this contains the reason why we define the service unit just like it is. And the way we did is, if we go back here, so what happens is we compute. We take into account the so-called TDP, or thermal design power of CPUs and GPUs. So what we said, we went and computed, okay, what is the energy consumptions for the power consumption of a CPU, right? How much a CPU node consumes in terms of energy, thermal design power. So the maximum, you can see that as the maximum possible energy consumption, right? Then we see, okay, well, what is the energy consumptions of GPUs on GPU node? And what we compute essentially is the fraction between energy consumption of a GPU node, energy consumption of a CPU node, and we compute this fraction here, this factor here, the scaling factor. Then what happens is what we charge is, what we see is, what it tells is how much it costs to run a GPU node, how much more costs to run a GPU node compared to a CPU node. So that scaling factor is the scaling factor that results in that 64 there. Essentially, what happens is that it works out that what works out is that based on energy consumption, a single MH50X consumes as an energy consumption that is like as an entire node of.
I see.
It's what we have a formula computed here. The weight, and we charge more proportional to how much more energy the GPU node consumes. There are other options out there, so you could actually look at not energy consumption, but you can look at peak performance. Let's say you can say, okay, a GPU is like 40 times more powerful than a CPU, then we need to charge 40 times more than CPU, or like 100 times even actually. And then, but that is not really fair to it's not really fair to users, because not everybody can achieve the peak performance of a GPU. It depends on the core. Depends on the core. So you are really penalizing people.
Yes, sure.
And then what happens is everybody says, I will go to use the CPU partition we run on CPU because it costs less, we run longer, but it costs us less in terms of service unit. And then what happens, do you end up consuming more energy, running for longer on CPUs, because CPUs are less energy efficient than GPUs. But if you charge them for peak performance, then almost nobody can reach peak performance. It's not convenient for people to do that. Instead, if you cannot, on the other hand, you could go on the other hand and say, okay, we charge them same as CPUs. It's not really fair, because GPUs in many cases give you a significant speed up. Might not be the best, you cannot reach peak performance, but you actually get a significant speed up for your code But if you charge it the same as, but it's also in absolute terms, a GPU is more expensive to run than a CPU.
Yeah.
So you're charging the same for a thing that is more expensive and is providing more power. So we cannot charge the same of the CPU for. And then people can say, okay, but what is the compute unit in the GPU? So how many compute elements are there? We can charge proportional to that. So some other people did that. I believe Gadi did the same.
Yeah, so that's what I was going to say. See, I'm working on a proposal for NT tomorrow, which we do every 6 months. So they have like two different numbers. If I understand, they have defined service units differently for GPU versus CPU jobs. So you have to basically, that's the kind of division they do. So they say that, okay, this many KSUs are for GPU jobs. This many are for this one. You can ask whatever you want, but the way we account for GPU dominant jobs is different from the CPU.
So what we came up with this energy consumption formula because it turns out that we want to encourage users to use the GPU partition when it's when it's convenient for them in terms of service unit, but also we want to drive them to use a more energy efficient approach. So what we did is we did a study. I don't want to delve too much into it, but what Maciej prepared this plot, and what it shows here is the application speed up on the x-axis, so a theoretical speed up for 1 hour execution, and then the max energy consumption of the job. Let's say, and we assume here for a job, but users decide whether to run on a CPU or GPU partition based on the service unit charge, right? And what you can see is that the energy-based model that we use brings people to use minimize the energy consumption, the cost, at speed ups that are slightly lower than other models. So what happens in peak performance model or serving or SN models means like charging for streaming multiprocessors in the GPU. So how many compute units are in the GPUs? So after a while, everybody is going to use GPUs. If you have like this type of speed ups, like 16, 20 times speed up, it's always more convenient to use GPUs. But in reality, many applications in the real life now don't have such speed ups. They have like maybe 5, 6, 10, 8. So in this case, with other models, peak performance models, for instance, users say, okay, but I'm going to use CPU partition because it's less. It charges less, right? And so they end up using more energy. It gets more expensive for us. But our model, that choice to use the GPU partition essentially kicks in earlier because it's turns out to be less expensive for users, but also less expensive for us because the energy consumption goes down.
So this is a number that application specific, and one has to know this by working on.
Yes.
You won't know that a priori.
Yeah, well, what we did when we wrote this paper, we had a few applications here, scientific applications, and we computed a few numbers here. So I think, out of memory, I think we have the CPU charge and how much we charge for this is the speed up, I think. And this is how much they would charge with GPUs, how much we would charge with CPUs, and then the cost ratio between the two. So, and we use benchmarks for this application. So it turns out that for these cases, in our model, users are encouraged to use GPUs because they charge less, and for us, it's more efficient in terms of energy consumption. And that's how we came up with those numbers. So
this is interesting. I wasn't aware of this paper, even though I think Bradley one point mentioned that there is such thing. And it's good. So it's on the archive, right?
Yes, I can say it's.
So the bottom line is that we should think not the same. We should not associate a 2 million core hours on Cetronics with a 2 million core hours on any other computers. They simply won't compare.
It's different currencies.
Correct. But my question was like lots of the supercomputers which are all like going for refresh, they also have to come up with a bit more
The reason why is like we started defining thing, there was no paper about this. So we were looking around and they said, we just put out our idea.
So some centers have gone on based on the speed up they got on the GPUs.
Yeah.
But whereas we got on the energy basis, so that's why it's quite a high number.
Yeah.
Gaudi charges only twice the CPU charge,
Yeah.
like for the GPUs.
Yeah.
But we went 64 times because energy is the main factor.
Yeah.
Because all the centers are now trying to be energy efficient. Yeah, it's all the CO2.
So that's what I was jokingly saying when when we were having this meeting. It's like currency conversion.
Yeah.
Essentially. Yes.
Okay, now let's move on to the next module, which is the job scheduling overview. So there are three modules back to back on jobs, which is the important one to see what's the difference between the Ganavarla. Yes.
So what I wanted to say is that as a final question on that, sorry, Leva, is that it charges more, but then use the same formula to compute the total available.
Yeah.
That's sure. Exactly.
So the fraction there is the same.
Yes.
It's trying to get the best out of those.
That's right. So anyway, so we will discuss that later. So yeah, thanks. I think that brings some clarity, definitely. Thank you.
So probably most of the users have been already attendees or have already access to the Ganavarla, so they might have run the jobs using the scheduler. So I'll try to make it a short one, this one, because the next module it's going to be important, trying to see the differences of all the different job types to submit. So in this one, we try to see what is the job scheduler, which everyone knows is why is it useful and what is the scheduler partitions and job queues. So to start with, we all know what is the job. So any work that we execute on a supercomputer is called as a job. So whatever the computational work, it can be a sleep command. Some people just do echo. So whatever the work we run on the supercomputer, we call it as a job. And the job scheduler is the one who does the program which manages all the work that is submitted to the supercomputer. So on a shared basis. At Pawsey, we have been using Slurm scheduler, which is by ShedMD for the last 11 years. So previously, I'm not sure whether anyone has used Pawsey resources before 2013. Anyone?
Okay.
So before we were using PBS, now since 2013, we've been using the Slurm scheduler. So it's going to be the same for I think in the likely future, near future as well. And we can see the picture here. So where the login nodes, so the users can able to access the login nodes, and from the login nodes, they submit the jobs to the scheduler, and the scheduler takes over and executes the jobs on the compute nodes. So people cannot directly, do anything apart bypassing the scheduler. So it's the scheduler which tries to get the best out of the supercomputer. It tries to make use of all the available resources in a proper fashion. So one important warning, which we always need to know, even on the Ganaval, it's the same thing. Please never run anything on the login nodes because they have limited users, limited resources, and quite a number of users will be accessing the same node at once. So if someone does anything, basically, if you take off the login nodes here, so there are two login nodes in this picture. So if you take them off, that no one can able to access the supercomputer itself. So that's why please avoid running any login compute intensive stuff from the login node. So how can we see why a job scheduler is so important? So here we can see this one. This was on a machine back in 2011 or 12, which I've been told like that. So it was an Epic system. It was a 192 cluster system, and tried to see how the resources have been, the scheduler is placing the jobs which were submitted by the users at different points of the time on a single day. So normally the users will submit the jobs with different durations and different compute requirements. Some will say, I want a job for 5 nodes for 5 hours. The scheduler will take it in, and then it will try to place those jobs in the resources as efficient as possible. So it tries to maximize the efficiency of the supercomputer. So it doesn't wait and not in the order of first in, first out, but it tries to squeeze the resources as it is available. So sometimes it's important to see how the scheduler is going. Sometimes if we are helping the users and if you're looking for resources, we look at the sinfo command and try to see, okay, the resources are available in such a fashion. So we try to adjust the wall time around and resource requirements around so that we can able to run the jobs quickly. And also the scheduler will takes one of the important thing is the allocations into consideration while scheduling the resources. If someone has, even the resources are available, if someone has exhausted all those resources, it tries to keep them out for some time, not immediately squeeze them in. So it tries to make use of the people those who have still have the allocation remaining for that particular quarter. So one of the best practice is to plan and organize your computational work with the scheduler in mind. So never try to wait for the jobs to run. Like when is it my job going to start? Try to automate as much as possible. I can see that MWA group has embraced the next flow. The pipeline, the workflow manager very nicely. So it does submit the jobs and then tries to use the automation tool so that let the scheduler do its job rather than waiting for the jobs to start. So you just submit your job and the scheduler will take over. So some of the things which we need to know, how a job priority. So whenever we submit a job, there are different things that needs to be considered taken into consideration. So there are the scheduler when this job is submitted to the queue, it looks at the job, it will assign a job priority. This job priority is based on say several factors. At the moment, usage relative to allocation. So how much of the allocation is remaining for this particular project, and tries to it increases and decreases the priority. It doesn't increases, so it keeps on decreasing based on the allocation usage over the period of time.
Okay.
And then also the wall time in the queue. So how long this job has been waiting in the queue for a long time. So it tries to clear the jobs as much as possible. So if the job has been waiting for long, it tries to increase the priority a bit.
Yeah.
So there is a wait factor, which keeps increasing as the job is in the queue. And currently the job size, the weightage on job size is missing on Cetonix. It's likely to be implemented in December. So based on if someone is submitted 1,000 node job, it gives a high priority for that particular job. Okay. Because the supercomputer is dedicated is to support high node jobs,
Right.
It's for high-end work,
Yeah.
not for the single core work. But you can try to modify your workflow so that you can able to make use of the job size in such a fashion, that your job will get proper weightage. Like rather than submitting single core jobs, you can pack them up into multiple nodes and try to run them. And also the important one is the quality of service level. So here we can see on the right-hand side, normally the middle one, green one, if someone has allocation up to 0 to 100%, it's called as a 100%, like it's a normal quality of service, QoS. But we allow some users to run up to, like every projects can use up to 10% of their allocation with high priority. So basically there is a directive called QoS minus QoS equal to high. So you can able to use 10% of your allocation for any important jobs, for any urgent jobs rather than requesting the help desk. Okay, this my job is very important, please run it. So you can use up to 10% of your allocation with high priority. And the highest one is you have to make a help desk request. So it's critical. So my publication is uh, I got a deadline for my conference, so I need to do my urgent work. So then you can raise a help desk ticket, and it goes through the proper channel, trying to get the approval as soon as possible. So Marche does the approval currently at the moment. So it tries to see whether it is reasonable to make the case. And if you have exhausted allocation, 100 to 150% allocation, you can run at low QoS. So that means you can still run. On NCI, once you reach 100%, it's cut off. You cannot do anything for the remaining of the quarter. So, but whereas we want to make use of the resources that are available, and we have got lots of resources. So at the moment, up to 150%, it's a low QoS, and over 150% of allocation can no longer run jobs. But it's not the case at the moment. It's yet to be implemented. But it's going to happen at any time, because once any project reach 150% of allocation, the main purpose is to make the people to understand how to request the resources rather than just randomly request and go over the limit. Some of the terminologies which we need to remember is the slum cluster. So all the resources that are managed by a particular slum daemon, we call as a cluster. So Setonix is the supercomputer and it has got its own slum cluster. So there is only one slum daemon which is running on the slum on the Setonix supercomputer, which is mapped to Setonix. So, and a slum cluster can have multiple slum partitions. So we call as partitions. Sometimes it's also called as queues. So partition or a queue. When we see the slum partition, so all the resources are divided, and a partition is the subset of resources with an associated queue of jobs. Like in a work partition has got its own set of queues, jobs, and long partition. So we'll look into the various type of partitions that are on Setonix going forward. So on for the CPU side of things, which is important to remember. So we have the work partition, which is general purpose for every users should be available. So at the moment, so 1376 nodes, and each node has got 128 cores. So yeah, you do the maths, the calculator, and it's a default partition. So if you fail to specify a partition in your job script, it will be submitted to this partition. So it will directly go and sit on this, and it's going to be a busy partition, like quite a number of jobs in the queue. So if you don't specify the partition to which partition it will go, you might have to wait longer. So based on your type of work which you are submitting, make sure to use the appropriate partition. And debug partition, it's basically for compiling, benchmarking, testing, and development. So, and the wall time is just 1 hour. So, and it's a quick turnaround. So we currently have 8 nodes. It's basically not to run production jobs. This is basically to test your job scripts. So we have seen in the over the period past time, people try to use this debug partition because it's quickly available.
Yeah.
And you can run only one job at a time.
Right.
So whereas a work partition, there is a certain limit, which is not on the top of my head. I think you can submit up to 1,000 jobs, but simultaneously, I can look into that later. So, but yeah, yeah. So high memory is the one, like the defaultly work partition has got 230 gigs. So in the documentation, you might see on the in the bottom, so the specification in the left corner, left-hand side corner. So specification, each node has got 128 cores per node, and the work partition has got 230 gigs of RAM. So, and this 230 gigs of RAM is equally distributed among those 128 cores. So that's what when Christian was presenting, he was telling you will be charged according to the request. Like if you suppose, if you say, I want only 1 core, but I want 10 gigs of RAM, you will be charged proportionately to the amount of RAM. So even the 10 gigs means roughly you will be charged for 6 cores. So even though I said only one core, but because you requested more memory, so roughly if you request a single core, you will get 1.79 gigs of RAM. Okay. So, and the maximum wall time on the work partition is 24 hours. So this is the default one. So whereas on high memory partition, we have the memory up to 980 gigs. So gigabytes of memory per node, so which is around 7.65 GB per core. So if your workflow demands large amounts of memory per core, yeah, this is the partition. But you can see the number of nodes that is available. It's only 8 nodes compared to the work partition. And the long partition, if someone wants to run a job for 96 hours, you can go all the way up to from 24 to 96 hours using the long partition. And copy partition, yesterday we have seen while trying to move the data in and out of the Pawsey center. So this one, there are currently 7 nodes because we have given 2 nodes to MWA ASO partition. So they used to be 9. Now it's gone down to 7 copy partition. So this is the high memory bandwidth nodes for specifically for data transfer. You can see this one, each core is roughly getting around 3.6 gigabytes per core. And another partition specific for our strategic partners, which is the ASCAP party, which is for ASCAP pipeline, and MWA as for copy partition. So which comes around 202 nodes. So basically, this is the CPU side of things. Coming to the CPU side of things, we have the GPU partition, MWA GPU partition. So there are 2 which we have recently provided for MWA for the migration. Is it going to be there for the rest
No,
of the time?
it's going to be, well, as far as I know, those partitions are not there for MWA before, and they represent the equivalent compute capacity of Caravarla, more or less.
Sorry, I didn't get that. So what is the?
So we have a few partitions there, the
Yeah.
NWA and WGPU partitions that are dedicated now for NWA operations, science
Okay,
operations.
awesome. What else?
That's the
So
understanding.
only one group will use, or everyone can MWA? Because MWA ops itself is one project.
So that, no, it's Bradley knows better this. It depends on, but at this point, I mean, WAVCS and WAXI have access to that partition.
Yeah.
And the jobs run on that partition just for those groups, they are not charged.
Yeah, I think these are basically like when you have a changes to the system or reconfiguration. That's what I'm imagining. But Bradley will have the right better information. So things that you might need to do very quickly to sign off that okay, system is now ready for thing.
Okay.
That has to happen quickly because otherwise, you know that.
The Caravan
Yeah,
will be
yeah.
deficient.
So for example, every once in a while when there is a site, you know, in these days, in the next 6 months, for example, lots of new receivers will be rolling out.
Mhm.
So there might be like situations where you have. I'm assuming that is probably it. But
Okay.
it's a small thing, but the way I look at it is like a things which you will do as like a quick test, engineering kind of a test. But these days you have to really look at the data.
Yes.
Another test.
Yeah.
Way of knowing like whether the telescope is really functional or not.
Okay.
Right?
I think this partition, like in the previous CPU side, MWA partition, MWA ASO copy, the last ones, and also MWA GPU partition
Yeah.
are going to be there for to support the MWA
Yes.
projects because they're equivalent to the Garavarla computational
Yes.
resources. Garavarla has got around 80 nodes and it gives a certain performance, but whereas these 10 and 10 will give the equivalent of that.
I think even slightly more.
Okay.
And yeah.
So for the GPU side of things, these partitions on Cetonic CPU partitions, they have 128 cores, whereas the GPU nodes have got only 64 cores. So, and there are 8 logical GPUs. It's called a GCD. Yeah, it's not a GPU, but it's a logic. GCD stands for compute die.
Graphics compute die.
Compute die. So there is a MI250X nodes. One GPU node internally has got 2 GCDs.
That's what
It's
we're talking. Yeah.
Yeah, that's right. Yeah, so you'll be, there are 8 logical GPUs. So yeah, when you request a single GPU, it's counted. You will be getting one of 8. And for the CPU side of things, there are 230 gigs of CPU memory, just like on the work partition, but you have the 64 gigs of GPU memory. So it's a more memory, GPU memory available per GCD and 24-hour wall time. And we have the GPU dev partition. I think it's likely to be reduced during the next maintenance. This 20 is going to become down to 8 because most of the projects have used those GPU partition for the last 2 years. Like it's for the test and development.
Yeah.
That's what. Yeah. It's like a debug partition just to support.
So which one at the top one?
No, the second one.
Second.
The GPU dev partition is just for debugging and testing purposes.
Development, yeah. It was there to support transition to Cetonics.
Like update projects.
Yeah, it's been 2 years since we had the GPU node, so I think the usage is not that high on the GPU dev partition. So we are trying to
move them to the normal GPU partition.
GPU partition. So that 124 is going to be 136 from December onward. And likewise, we have the GPU high mem partition. The GPU memory still remains the same, but whereas the CPU side of things, it has got 460 GB memory per node. So that's the CPU memory is 460 gigs, whereas the GPU memory is still the 64 in order to support certain workflows.
Any questions so far online?
Yeah, please raise your hand or if you have any questions. So, okay, keep moving. So in order to query the slum partition, just like on Garavarla, you can use this command called sinfo. So basically sinfo will give you the list of all the partitions and what is the status of each and every node and what is the wall time and everything. So in the next slide, you can see this one. So when we ran sinfo, it will show work partition several times, but there is a meaning for each one. So, but the state it can see. So these first two lines they are down, or one down. So mix is the like multiple jobs like are accessing this particular node. So mix means it's a mixed state. That means different jobs are running on the same node, and some nodes are idle and allocated will be there if they're all allocated in exclusive fashion, which we'll see in the next module, why it is mixed and why it's allocated. And again, the ASCII party, which is for ASCII operations, debug partition. So you can have, SINFO will show what is the maximum time you can run on those partitions. So on work partition, you can run up to 224 hours. And you can say the availability, is it up or down? So if it is not available, it will go, stays down. The next one is the SQ, which is a popular command. You might have used it several times. It just to queries the job scheduler, the queue in the job scheduler. So currently, because Cetonix is currently used at around more than 2,000 users, you might see a lot of jobs suddenly at once. And so many people are using the Nextflow pipeline, so it submits jobs like, literally we have already reached billion or something more than a billion. So in the last jobs that are submitted. So in order to reduce the thing, you can use the head command or the less command or the word count just to see how many jobs are in the queue. Likewise. And if you want to say, okay, I submitted my job to the work partition, so let me see what is the jobs in the queue. So you can specify SQ minus partition work. You can only see that jobs in the work that specific partition. And minus me means that are the jobs that are submitted by yourself. Likewise, you can specify, okay, you are the PI and you want to see who are submitting the jobs to this particular project. You can specify minus account to see who are submitting the jobs. And you can also query other users' jobs as well. So if I want to see what someone else is running, what Sam is running, I can say SQ minus user Sam. So you can able to see his jobs like, but of course they cannot able to access what they're running. They can able to see what. Yeah, we try to limit that particular.
Yeah, and so at some point there were controversies on this feature because then people complain it's running too many jobs. I cannot use the queue.
Yeah, they're trying to complain. Okay, some users are taking over the control.
Yeah.
But from the Slurm side of things, it's not possible, like, to restrict
too limiting for us to do actual our work to support users.
Yeah.
So it was not accessible. Well, not possible for us to limit that view.
Yeah. So some users are complaint like, I don't want other projects to see my jobs.
May not be able to do that, but I think it might be possible to have some guidelines that people are expected to follow. Not just encourage, but it's it's like sort of a mandatory kind of a thing. And sometimes I look at these things, supercomputing facilities like national facilities like telescopes. We write the proposals, we get time allocation, there is a tag and everything, right? And of course, there is also other support. But there are certain things I can't do just because I have time. If I go to parks or DMRT, I get training, and there's certain things I'm allowed to do, certain things I'm not allowed to do, right? Because it is a shared resource, it is for everyone.
Yeah. So that's what you can do. And by default, you will have a certain format when you run the SQ command. So here you can see the format is job ID, partition name, user, ST stands for status, time and nodes, how many nodes that particular job is using, and node list, like what are the nodes that have been assigned to the particular job. So you can change that particular format by specifying minus format, and you can able to see that SQ underscore format also, if there is a shell variable which specify that you can modify that one and you can add. So according to your thing. Moving forward, so in the status thing, probably the important ones which we have to notice is R stands for running, PD means pending, CG means completing the job is completing state, F means failed. And also the other status is a dependency in the node list. The reason it says dependency, that means that this job is dependent on a previous job which is already running. So unless until the job completes, this next dependent job won't run. Yeah. So here is an exercise. We can run through it, like, because you got an accounts, but if you have anything. So how many jobs are currently queued on Setonix? Basically, you can use this pipe command, sq pipe wc minus l. So you can specify how many jobs are there. Sometimes it goes up to 5,000, 7,000. It depends on the load, how it goes. And if you want to specify, I want to see the jobs that are only for the partition, sq minus p partition. How many jobs are currently queued in this partition? You can say sq minus p work by wc minus l. So, and list the jobs that are only in the queue partition. So it's a pretty much straightforward. So because you've been users of Slurm for quite a long time, I don't want to spend time on taking. So basically the answers are on the next slide. So sq wc minus l minus p work, yeah, minus p copy. Likewise, you can able to specify, I want to see that just one user is trying to, yeah, I admitted. Okay. So I want to see the jobs that are submitted by myself. So sq minus me, and then you want to see the job that is submitted. You will, when you submit a job, you'll get a job ID, and then when you run that command, you will see this. There is a job in your under your sq command. So basically, in this small module, of course, I've taken a bit of a long time. We learned about some of the terminology, just a refresh of the terminology, and sinfo and sq, and yeah, we noticed that we should not never run on the login nodes and try to plan your work and try to do the automation as much as possible. And do not sit before, keep on running sq command and say, oh, when is my job running? It's a scheduler does the work. So even if you sit before the computer for hours, it doesn't start. But basically, you can see the slum sinfo command and try to see, okay, the resources are available in this partition, or if I minimize the time like this, I can get.
What else is trying to be as accurate as possible when you request the resource you want?
Yes.
And the time, especially the work time, so that there are gaps to fill in the schedule. So if your job takes 2 hours, it's more likely to be scheduled before than one takes 24 hours.
Yeah. So yeah, that's right. Yeah. We're going to see that one in the module 10, how we can specify that one. So yeah, what Christian said, if a job is running for 2 hours, and if you specify alternate 24, scheduler doesn't know that your job is going to finish in 2 hours. It just sees the 24 hours. Yeah. So it tries to see when it is available for 24 hours. But if you specify for 2 hours, you can specify 2.5 hours, like just as a bit of leverage, then you can able to get it. Scheduler say, okay, it's a small job, I can fit in. Okay. So moving on to the next one, which is module 9, the running jobs. It's a quite a long, big module, so with 40 slides odd. So, which because we are seeing all the different things, and after this module, we can take a break. And if it is taking longer, we can take a break.
Half an hour,
yeah.
10:30.
10:30, we can take a break. Yeah. How is it happening with the online participants?
How is it going? Everything right?
Can you guys hear us?
Yep, all going well.
Okay. Yeah. Please raise your hand, and if you have any questions, immediately. Coming to this module 9, which is project running jobs, we're going to see what is job script. Sorry, I've been used to this particular called job script. It's also called as batch script. What term do you use, Christian?
Batch script.
Batch script. Yeah, it's been, job script is the one which I've been using for the last 10 years. That doesn't come out of my, because, batch script. In the documentation, we use this term interchangeably, batch script and job script. So, because the script that is used to submit the job, so that's why job script, and it's called as a different thing. Coming to the submitting and monitoring jobs, a quick couple of definitions here. I just added this particular also referred as on master because I cannot come out of it. Yeah, even when I was a couple of years back when I was presenting, I was keep on saying job script. So yeah, it's been inbuilt in me. So yes, excuse for that one. So if you're using batch script, that's good. But so batch script is basically it's a computational work that is submitted to the scheduler. So it contains the instructions which is read by the scheduler and also the commands to execute, which we all know that one. So commands are commands to execute are written in shell script language. So it's a pretty Linux style where we use the bash script to submit the job. So all the commands which we written as hash sbatch. So normally in bash, if anything starts with a hash, it's a comment we can read. But Slurm, if it start with hash sbatch, Slurm reads those scheduler commands. Okay, these are for me to request. The user is asking these resources. And some users, they provide this sbatch directive as a command line to the sbatch command, like rather than specifying in the file, they provide to the sbatch command, sbatch minus minus time equal to, and all those things. But the important best practice is try to keep those requirements within the batch rather than on the command line. Does it make sense? Like, rather than making a big command line sbatch minus minus time and minus minus end task, because it's not possible to type all the time. So, but if you put it in the batch script, it's a reproducible. So we can able to, other users can able to get the same thing what you're getting. And it's a bit of unless until you provide the proper sbatch command. And also whenever you request our support from us, if you proper job script, then we can able to quickly assist. So there's a demo which let's do together, but this is further, but we can have a quick look. So sbatch. So how do you submit a jobs batch script? So using the command sbatch followed by the batch script name. So that will be submitted to the scheduler. In some of the trainings, we provide the reservation. So this is what I'm meaning, like, don't provide to the command line, like sbatch minus minus reservation. But this is an exemption because minus minus reservation is one-off use because we don't provide reservation every time. So, but if something that is quite common, trying to put them within the batch script. If it's something one-off purpose, then you can put it in the command line. So, and so this is the exercise. So if you want to refresh yourself, you can run it. And if you see any issues, please let us know, or else you can raise a help desk ticket saying, like, this particular exercise is not working. We can look into that. So basically the exercise is quite simple. So we are all the simulation data. Yesterday we have seen the Scratch is for working data. So that means if you're running any simulations, please go to the Scratch directory, not from home or from the software directory. So, and you can git clone this repository and go to the repository directory, and inside you'll see a running jobs. And then you can submit this directly as batch submit underscore monitor.sh. And then you can see that the job is submitted under your account. So SQ minus me, minus minus me, it will say the job is submitted. But after a while, this is disappeared because it's a pretty small job. It's just to see. So you can able to cancel the job using scancel command. So it's a pretty small exercise for the new users. This is the training is being organized for, but if someone wants to give it a try, please go through these exercises.
I will suggest clone your repositories on my software because that is the scripts, not the Scratch. Then you will write the data on. But this is not made to the training team. Because you want to clone your code repository in my software. It's the data you want to on Scratch.
On Scratch. Okay, yeah.
This is a simple exercise.
This is a simple exercise. That's why. If you want to your git cloning, as Christian said, put it on your my software and then copy the data across to the Scratch when you're running the job. Because otherwise, unless until you want to git clone each time, which is sometimes big. So the answers for this one is also there. So basically that particular script is printing the host name a couple of times. Like there is a sleep command at every 15 seconds it sleeps and then prints the thing. And here is scancel. When you cancel a job using scancel command, you will get this particular message in your the Slum output file. It says, oh, this particular job has been cancelled at so and so time. And job hitting the time limit. So yeah, and we have an exercise here just to demonstrate if you don't request good enough to time, like for your simulations, you will hit the wall time limit, and then your job will terminate halfway through the job, or not halfway through, before completing. So that's why it's very important to request the uh, appropriate wall time for your thing. Don't over exaggerate or don't underestimate the job, like overestimate, underestimate are the two things. But if going into reasonable, if you estimate, okay, the job is running for 2 hours, going around 3 hours is okay.
Okay.
But rather than 2 hours and 1 second, that's too ambitious. So because sometimes Slurm takes a bit of things around. Some of the common error messages which you might come across, probably some of you have already come across this one, which is the segmentation fault. Currently, I'm helping a user with the same issue, because there is insufficient memory for the workflow, because it's a machine learning job running on with VASP, and VASP doesn't run on GPUs. On CPUs, it's trying to help the users. You can see if you do SQ minus user, my username, you'll see the job which is currently running. So it's basically helping the user. So if you don't spell, if there is insufficient memory or if there is invalid memory access, you will get into this segmentation fault. And sometimes if there is not enough memory for your processes, even if one of the processes, then you will see this OM, out of memory errors. So it will say, okay, you have requested insufficient memory. This is the reason. So which is the two common error messages which people come across with their workflow. That's why when something goes wrong with your job, please check the output file. Don't say, I got an error. So in the previous years on the help desk, we used to say, I got error. So what error? Then try to provide information, try to see the job script and try your Slurm output file and see where is missing. Right. And that's why nowadays, if you raise a help desk ticket, you will automatically get a message saying, okay, can you provide the job ID, username, path and everything? Because sometimes we have this strange request. I got error. So that's it. So without providing the context, like most of the error is is in the output file. So it will show you what is going wrong with the particular jobs. So if you want to detail about the queued and past jobs, there is a command called scontrol show job ID. So if the job is currently in the queue or if it is currently running, you can able to use this command. But if the job is already finished running, then you cannot use this one because the job is already finished. So this scontrol show job ID will give you the detailed information. It's maybe 15 to 20 lines of information. It will print out on which node it is happening, which user is submitting, what is the path, what is the Slurm command they are using. So all the different, very detailed information that is being provided. Please note, yesterday we have mentioned this one. Each node has got 128 cores, physical cores. But this advanced CPUs have got as we call as the hyper-threading, or also called as simultaneous multi-threading, where one physical core is acted as two logical threads. So, but the Slurm, here in the warning you can see, sometimes you'll see, oh, I requested only one core, then why am I charged for 2 cores? It's because the Slurm, it's being turned off on Setonix, disabled on Setonix, but the Slurm still sees that value.
So what happens is the final charge will be hard in the accounting. So because Slurm sees 256 cores, but then we charge only for physical cores.
Yeah, we divide them by 2. So if you're using say 1,000 core hours, you'll be charged for only. In reality, Slurm sees 1,000 core hours, but we charge for 500 core hours because of the hyper-threading.
So hyper-threading is something only Slurm will report.
Yes, Slurm sees.
You will not see it in the. I think it's something if you dig in the billing system of Slurm, then you find this particularity. But this is correctly when we do our counting on our side in our database, we divide it. But we divide it.
So is that a direct indication of the efficiency of what you are submitting?
No. when we have this tool, we will show.
SEFF, which assumes the use of hyperthreading. But even in this S control show job ID, I can quickly demonstrate because it is. Can everyone see this one? So here I'm quickly doing SLOC minus debug minus n tasks equal to 1. I'm requesting only one task, but if I have the habit of before submitting, I'll run my command. It takes time, so that's my job ID. So S control show job ID.
Well, I think it's okay.
Yeah, it's allocated.
Maybe you can increase the font.
Okay. So here you can see when I run this one, S control show job ID. So here you will see this one. I requested only one task, but here num CPU sees 2 because of the hyperthreading. So don't get confused. Okay, why am I looking at 2? Yeah. Even the billing is saying 2, but our Pawsey account balance, probably you might have mentioned this one, Pawsey account balance. It's basically a bash script. So there is a thing called HT factor. So you can see HT factor equal to, for set on X, it is HT factor equal to 2. So basically we just divide. So, sorry. So for set on X, we can have a look. So basically raw usage minus HT factor, that is basically dividing by 2. Yeah. So you'll be charged only for the physical core usage, not for the entire thing. And now if I complete this job, and there is a command which I mentioned in the warning here. So what is the efficiency of, because I didn't do anything, but if you can see the efficiency of the particular job. My efficiency is so poor, like 0.5, because I didn't do anything with my particular allocation. So here you will see again too. I requested only one task, but yeah, don't get confused because it's because of the hyperthreading. Yeah. And the CPU efficiency also counts the hyperthreading. So suppose if you see 40%, you basically have to double it. So 40 becomes 80%. So you can say, okay, my job efficiency is 80%. Well, in this case, it is 0.59, so it is roughly around 1.18. Yeah. So percentage efficiency. Okay. Now coming back.
Also, this command, it doesn't really work for the GPUs, I think.
It doesn't work. Yeah, that's a good.
So that's so this command is okay for CPUs, but for GPUs, it doesn't take into account.
Yeah, it's all In GPUs, it's at we need to. Have we got any other thing? Yeah, we had to at the moment rock MSM. I try to use the energy usage. Monitor the. Yeah, here you can see to see the energy output for a specific job. You can specify how much energy has been consumed, and you can see what is the ideal one and what is the consumed. That is important for the GPU jobs. So SCAMP is another important tool. Now this particular command S control show job ID. So now I completed the job, right? So I terminated, I exited. So my job is not running. This particular command is only used when the job is queued or running. But now if I run the job, you can see this one. Oh, still there. But after a while, it basically disappears. Yeah. I'll just do any other job. So which is no slum output file. Yeah.
Maybe it's actually.
I mean, no, I'm just trying to say that particular thing will not work if I try to do it on a S control show job ID. So you can say invalid job ID specified, because this particular command is only used for the jobs which are currently in the queue and which are running. But once the job finished completing, so you won't be able to see the information on that one. For now, in order to see the information, we have to use this command called saccount, SACCT, and I can specify the job ID. And now I can see all the different information. So there is a lot of information you can specify. I want to see, okay, what is the elapsed time? How long did I run this job for? How many CPUs did I allocate? What is the state? And what is the start time? What is the submit time? You can all specify all the different things. So there are quite a number of fields. Your go friend is man pages. So if you want to specify man as account, you can able to see what are the different options that are available with this particular command. So you can able to specify all the different things. Yeah, here is the important one. So all the different, so which account, all the different things. Okay. So here, when I specify this particular job ran for 1 hour, and then basically the state is timeout. So because I requested a debug partition on, I ran it for 1 hour. So 17 seconds is a bit of a leverage, like a slurm goes a bit extra. And I requested CPUs. So basically I requested 2048, but because of hyperthreading, I'm seeing 4096. Sorry, my mouse is, where is it sitting? There is a bit of a lag when I'm doing, like, yeah, this 4096, basically I requested 2048 because of hyperthreading. So don't get confused why it is double charged. And moving on, so S account and S control show a job ID. They're the two important ones which you can specify. And if you want to see a job within a particular time limit, like, okay, I want to see a job starting from the start of the year. Okay, what jobs did I submit? So you can specify -S, or if you want to end with the time limit, so on what time format, -E means -end.
Yeah, by default, SAT will only show you the jobs of the current day.
Current day, yeah, that's
and
right.
then in the current day, but if you want to look at jobs in the past days, you have to specify a start date where it since when you want to look at.
Yeah.
But
So
also don't ask too far late.
Yeah.
If you don't specify a job ID, because otherwise it crashes.
yeah,
And I know that personal experience.
yeah, within a year is okay, maybe. Yeah, some users they have some.
But if you have many jobs, if you ask for all users, I was trying to.
Yeah, that's right. Yeah, don't do for all the users on Setonix. I want to see
Yeah.
all the jobs from the start of the year. That's putting a hammer, like, breaking the slurp demon itself. Like, it has got limited resources, but we are asking a compute thing. So try to ask in a reasonable way. So maybe what are the jobs did I submit from the start of the year?
Okay.
Or like what of my student, one of my student, I want to see all the different things.
Yeah.
So this is the S account format, which we already seen in the demo. Another one is the SLOC. So by default, S batch is recommended. That means you submit the jobs to the background. So everything done by the scheduler. Sometimes if you want to do something interactively online, like in the live interactive session, you can use this command called SLOC to start an interactive session. And it has the same options as batch. So whatever, but you have to specify in the command line SLOC -- and task and everything. This particular format for job submission is recommended for debugging, compiling, because you cannot debug a thing which is running in the background. So you have to be able to see what is happening, or if you want to compile or field processing. So yeah, because I ran the exercise like one of the demo using SLOC. So the same thing will happen here. So you can. So how's the time?
10:28.
10:28. So because I'm going to the next part, which is important one, writing batch script.
Okay, we can take a break now.
How about online participants? 10-minute break. Let's see at 10:40.
We will have a break for 10 minutes.
Yep, sounds good.
They're already having a
Okay.
break.
No, somebody said yes. I don't know who. They probably have.
Okay. Yeah.
They are multitasking.
Yeah,
Some of us,
that's what happens here.
which I can't do.
All right.
Multitasking is basically switching between tasks, right?
Yes.
Because human brains cannot parallel process. We
Exactly.
can only do one at a time. When you say multitasking, a lot of people, I think people say I'm multitasking, but you are only switching between
Yes.
one task to another.
Yes. It's concurrency.
Okay, someone else. Okay, good. We'll get back to it, Bradley, after when I use it.
This account command.
Yeah, so
Yeah.
specify to that one.
That's quite a long question. I'll check it out.
Yeah, we'll get back to. Oh, why is it going on Windows?
Because you are saying it happens. Nested loops.
Because I zoomed it
Yeah,
and dragged it.
yeah,
It's
yeah.
again. Oh, okay.
Yeah.
Oh,
That's the scanning.
will it stop forever or go?
No, you just change the screen and it will stop.
Yeah, because you're sharing your.
You're sharing your
thing.
yeah.
Okay.
Yes.
Stop sharing.
Hmm.
Yeah, probably.
This one is already sharing.
No, the problem is that because you're looking at the screen.
Yeah.
So if you just go to the chat, then you can see the chat.
Okay.
Yeah, I will check the chat.
Yeah, we'll come back to it. Yeah.
Yeah.
Yeah, you can see that one. Yeah, they're nice.
What code is here?
Yeah.
I don't know. What we need? Probably it's better to use the. So we were muted, yeah. Now we are back.
Oh, so Bradley may not have heard it.
So we were muted, right? So we are sharing code.
Oh, is it?
I was talking. I told you the room
No,
was
what
muted.
is happening?
Bradley may not have heard it.
Yeah, Bradley, we'll try to provide it like, in our documentation, what you suggested that are needed for the people. It's a very important one. So just
Yeah, it was. Hopefully you can hear me. It was something that I kind of had to kind of come up with myself, basically just looking at the man page and some online documentation. But given that the requirements for the merit allocations and that kind of thing, and even for just general use information about how efficient are my jobs being, just having sort of those standard numbers, be able to just copy paste this into the terminal, give it the job ID, and here's the numbers you need, is super useful. And otherwise it's a bit of a barrier to people who maybe don't even recognize ESSECAM exists, or that you can do this kind of thing with it. But yeah, it'd be great if it just is even just part of the application page, or just in the documentation in general.
Yeah. Moving on to the next page. Is it coming through? Okay. So writing batch script, which you all got experience working on that one already. So quickly go through the couple of programming models, which is two dominant programming models, parallel programming models in terms of the CPU side of things is the distributed memory parallelism and shared memory parallelism. So probably you might have heard about MPI, which is the message passing interface, where what happens is you will be dividing the entire computational workflow into different chunks, and each processor will be working on a chunk of that problem. So you divide this, your grid size or whatever the problem, and different processes will be allocated to each of them and try to, and sometimes they have to exchange messages between each of the processes, which is done through this specification called MPI. On Cetonix, we have the Cray MPitch, which is optimized for the on Cetonix to make use of the interconnect. But if you are using OpenMPI on Garavalla, you might not be able to see a good speed up when going across multiple nodes. So it's better to recompile your code to make use of the Cray MPitch MPI implementation. Yeah, so we have users using Intel MPI, OpenMPI, but the speed up across the nodes is terrible. So, and the other one is the shared memory parallelism. So now you have in the distributed memory parallelism, so you have your entire workflow divided into different processes. And if the one of the process, like the processor taking too long in one of them, so you can throw in more number of cores, we call as threads, trying to speed up the computational intensive portion of the code. So if the one of the some part of the code is taking too long, you can throw in more number of threads, like multiple concurrent threads to efficiently, quickly speed it up. Achieving a shared memory parallelism in the code is quite simple, but whereas distributed memory parallelism is I used to hear about this one, it's like a crossing the desert. Whether you reach, unless until you're very confident of your workflow or of your code, achieving the distributed memory parallelism takes a bit of a time. Whereas shared memory parallelism, you can quickly identify with the profiling tools. Okay, this particular for loop is taking too much time. You just add in a couple of lines using OpenMP pragmas, and you can able to quickly speed up. But the problem with the shared memory parallelism is you can able to run your code on a single node, because you cannot share the memory of another node. So you can share the memory of a single node. So the shared memory parallelism is easy to achieve, but it's limited in terms of
easy in most cases. There are some cases where, depending on the algorithm you're doing, but in general, it's easy.
You can achieve, But whereas distributed memory parallelism, you can achieve the scalability across the entire of Cetonix. So we have seen the work partition as 1376 nodes. So some of the codes at Pawsey, which are currently running, they can smash the entire Cetonix. They can use all the nodes. But in order to achieve the thing, because you basically try to divide the workflow across the multiple processes, the messages, communication, and talking. But If you are the owner, like, if you have written the code by yourself, you can able to achieve. But if you are trying to parallelize someone else's code, it needs a bit of an expertise, like, or time. Like, yeah, one of the person says it's like a cross interface. When I was learning MPI, so people have said, oh, it's like a tacit, like you have to be very sure of each and everything, how they need to be communicating.
It's also depending on the science case, or depending on as a group, like you don't have to write your own code. There are professional codes written for that you can just simply run. Then it's matter, you have to organize the computation. But in case, you have, for instance, molecular dynamics, we have VASP or LAMPS, and we have a few established codes that people can use, right? So in the case of you developing the code, we are talking specifically in developing
this
the code.
Developing side of
developing, if you're developing your own code, then doing that can be challenging. But we support applications that are widely used. That's why we sort the system wide. Everybody can use them. And if you look at the percentage of usage on our supercomputer, I think in terms of number of applications, a lot of people are using these third-party
open source codes,
But for instance, Igor is writing his own code, and his code is like parallelizable across multiple nodes. And
you can ask Igor maybe how was it maybe 20 years back, how did he find? He started basically on a single node, and then he presented in one of the talk how it was evolved over the time. In 2007 or 8, one of the Pawsey staff supported and shown him the distributed memory parallelism. Then it started scaling across multiple nodes. Then Maciej came and helped him with the GPU side of things. Then it's evolved over the period. So initially started with shared memory parallelism. So.
But I mean, just out of curiosity, because you guys must have seen and worked with him. But Igor, yes, that's a lot of computation is there. But the big difference between that and the kind of MWA processing we do is like we also dealing with a lot of data, then we have to stitch them together.
Yes.
I think that is where I think a real big problem is.
Yes.
Because if it's like you have a tons of computation, you are just very efficiently distributing them. And yet, like yesterday, you said some of his codes are like even in Fortran, and which is like
he's doing simulations and producing data.
Those things are
data analysis data from it's different. Depending on the workflow.
Right. Say for example, even there, that even if you are using like MPI, things are distributed, you can still collect it and do it. But with the data related things, which is more like things like BCS beam is essentially telescope backend, time critical task. That's where I think things are getting interesting.
The data parallel. So you need to see not the compute parallel. So so it's just a definition like a GPU accelerated parallelism. So we have different programming models like on NVIDIA, probably on Garawala with NVIDIA GPUs, you might have used the CUDA, but on AMD Cetonix, it's AMD GPUs. So the programming model preferred is the HIP, and also the OpenMP for target offloading is still available on Cetonix, OpenACC, and OpenCL. So this GPU offloading is basically designed to process large blocks of data in parallel. So it's a compute parallel, like it just the auto speed up is quite efficient, great in terms of compared to the traditional CPU parallel programming models. Here is the sample batch script, which we can see here. So it is in the exercise documentation as well. So typical job script, you have a start line is called the shebang line. So that's how the Linux will recognize it as a bash script. And -L, we'll see all of the different things. And hash sbatch, the Slurm scheduler will able to read those things and try to say, okay, these are the resource requirements. So we are asking the Slurm, okay, I want one task from the work partition, and that is one task per node, and CPUs per task is one. So basically, I just need a one core. We are telling the Slurm, and Slurm will allocate the resources. And at this later part, so we are basically using those resources. So this is called the requesting the resources. This part is the using the resources. Currently, we don't have the SRun in this one. It's a basic example which we are running the echo command. The host name is host name, and then sleep for 15 seconds, and then do it a couple of times. So -L, the first line, it is the important one. So sometimes It's not reproducible. Sometimes you might get the correct answer, but sometimes it's recommended to use minus login or minus L in order to fully get the shell environment correctly for the job. Like, it's sometimes creates undesirable behaviors. Like, it's a good practice to always use minus login. And the other part here is the commands which are executed on the command. So basically in this part, after the directives, don't intermix, like, the directives, let them be after the first line. All the directives should go after the first line, and then the real command. So in this part of the program, you can have the like loading the modules, and you can configure the containers, you can provide some variables in order for the job to run, all the file like post processing and like copying the data across all the different things, and the finally the command. So here we are basically doing a simple stop, but we can see this is the part after the directives. You provide the module loads, commands, or like file variables, like pre and post processing stuff, and finally the execute command to use those allocated resources. So to have a quick look at the SPatch directives, the important ones are the job name. It's optional. It's not mandatory, but it's important. Otherwise, if you're submitting thousands of jobs and if everyone has got the same name, you might get lost into it. Like, you can able to specify, able to see which job is currently sitting in the schedule, how it is sitting. And the account is important if you're part of multiple projects. If you are part of only one project, it's an optional one. And if you don't specify, it will pick up the default project that is currently in the Pawsey project file.
There is one exception to that rule we will see for the GPU jobs. For GPU jobs, you will have to specify your account dash GPU.
Minus GPU.
Because as I said in my previous talk, we have two different accounts for CPU and GPUs.
Yeah.
So the default will be the one you have in your script, but then for the GPU jobs, you will have to specify the.
Yeah, maybe it's because I noted that one. I updated the slides for the later part of the session, but it's the first, since we are starting it the first time. Maybe Christian, we have to update this part. Yeah, I remember that one. And then partition, which partition you want to submit your job to. Otherwise, if you don't specify, it will take the default partition, which is work partition. For GPU, the default will be the GPU partition. Yeah, because if you go enter into this default, there will be more jobs when compared to the debug partition. So if you want to just debug for 1 hour, and if you don't specify the partition, you will be waiting for longer in the work partition. So it's important. And if you don't specify the time partition, by default, it will take it as 1 hour and your job will crash. So it's better to.
I think the suggestion here, you don't rely on defaults and just specify as much as you can.
Yeah, the time is important. Yeah, sometimes like, you can specify a single request like minus task is enough, but
this will come with experience as well.
Yeah, time is important. Important. It's not mandatory. If you don't specify, it takes 1 hour. So it will run on Lumi, which is the Finland supercomputer. If you don't specify time, it gives 1 minute. Yeah, it happened because on Setonix, normally we help the users. I don't do production jobs. So we do jobs without specifying the time directive. After 1 minute, it gets crashed. I said, oh no, because that habit is there without specifying. But as the researchers, you always need to specify the time so that it's right, runs for the correct amount of time. In the next module, we'll see how to specify the time, like what is the reasonable way you need to do a bit of benchmarking. And QoS, it is currently not shown, but I mentioned that particular QoS, we have the different QoS levels. By default is a normal QoS. If you want to specify, if an urgent job is there, you want to specify QoS equal to high, you can specify, okay, I want to run the job with the high QoS. Up to 10% of your allocation, you can run with the high QoS. By default, it's a normal QoS. Other directives, important ones, end task equal to is the number of parallel processes you want to run. It's used basically for MPI, message passing distributed programming models. If we don't specify, it's again defaults to 1. End task per node is how many number of processes you want to run per node. So remember, on Garavala, you have 40 cores per node, but here we have 128. So it's better to request in the multiples of 8. We'll see in the next module as well for that one. But if you don't specify anything, it defaults to 1. Always specify it, otherwise you will be more than. And CPUs per task is the number of threads you want to launch per process. This is important for the OpenMP programming models or the hybrid MPI/OpenMP models. But always remember, whatever you request here, like whatever the numbers you specify in the directives, n tasks per node multiplied by CPUs per task should be less than or equal to 128. If you specify more than 128, the Slurm will say, sorry, the resources is not available. So it's not possible. So you need to make sure that whatever the thing. One of the other directives which we have not mentioned is the minus nodes. But if you're very sure about these particular directives, you don't need to specify minus nodes.
Right.
That means you can have a backup. You can specify the minus nodes. Yeah, some people say dash, but I use the nodes directive. So suppose if I'm requesting 128 processes and 128 tasks and 128 tasks per node, then you can specify minus nodes equal to 1. It's a default one. So suppose if I'm requesting 256 n tasks and 128 n tasks per node, Slurm will say, okay, it's basically this guy is asking for 2 nodes. It does that.
It's also, I think there's some implications in the fact that what if, your tasks, you don't have 2 full nodes available, but, you have a number of tasks that would be equivalent to 2 nodes, but there are no 2 nodes to accommodate those tasks, then they have to be distributed across more nodes.
Yeah.
So in that case, it's if unless you're using exclusive in terms of you want the whole node, then you just specify a number of tasks, and then the Slurm will find the number of nodes required to satisfy that request.
The Slurm will do the maths behind the scenes. Okay, if you specify, okay, I want this number of tasks, CPUs per task, it does, okay, basically this user is asking this number. Yeah. Another one is the directive is the memory mem, which is an optional thing. But suppose if you have some of the workflows are memory intensive, so I want only one core, one task, but I want more memory, then you can specify minus mem equal to this much. You can specify as much. But as Christian pointed in his module, the accounting module, it will be charged according to the highest of the resources. Yeah. If you request more cores, it's proportionally will come, but if you request more memory, it will see the proportionate amount of cores will be charged.
Okay.
Yeah, so I think some of the MWA workflows needs more memory than 1.79 GB per core. So you might be using this directive more or memory. So another important one, I know some of you might have accessed Magnus. On Magnus, which was the previous supercomputer at Pawsey, it was a Crane supercomputer before Setonix, where each node is allocated on exclusive basis. Like if you request a single task, even though you request a single task, you were allocated the entire node on Magnus.
It had 24 cores.
24 cores. But whereas on Setonix, we have 128 cores, and we have changed this node access mechanism. Now it's called as a shared node. You will be asked for the number of cores you are asking. You are not charged for the exclusive. But there is an important directive which we'll see in the next slide, which is the if you specify that one, even though you request one task, you'll be charged for the entire node. So exclusively you're asking for the entire node. So the exclusive is for the node.
Yes.
No, not for the task.
It's for the nodes. You're asking the exclusive usage of the node, whatever nodes you're using.
But that could be due to because you want more memory or all of that memory.
All of the memory, all of the resources on that. So you don't, if you want to see a predictable performance, suppose on the shade one, which here, so your jobs might be placed on anywhere on the node. Yeah, it can be based on other jobs, how they're running on the same node. If there are 20 or 30 jobs running on the same node, you might not see the same performance each time in the shade thing. It depends on how the other jobs are
doing. One thing you cannot control in the shared environment is, for instance, the usage of the network.
Yeah.
So, for instance, there's other process running a network communications, and then you are shared the same network
And
cards.
also the
that may
memory
have
bandwidth also is shared.
bandwidth,
Yeah.
So you
may
won't get the
want your
same
own
thing.
node if you're using fully, no?
Yeah. So, but in the coming
Okay.
to the later slide, so there is an important directive here is called minus minus distribution equal to block block block. So the first block is for the CPU. Like there are two CPUs on each node, and each CPU has got 64 cores, and each core, like each socket has got 8 CCD. So it's a placement. So block, 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 it's a CPU, socket, and CCD. Like yesterday we saw the core chiplet die.
So it's basically on the high level, it's a way of distributing the tasks, the processes on the various cores.
Yeah.
And
the on the contiguous, like, rather than spreading the thing. Yes, Bradley, yeah.
Oh, sorry, you could finish your point. I was just going to say there's actually a really good example of this on the documentation of how to do that. And Ramesh, for your interest, I have a example script that does this for a dedispersion plan where it actually splits up with this distribution approach and does the dedispersion plan all in parallel with one job. So anyway, sorry, I just wanted to note that.
Yeah,
that's fine.
Yeah, I was basically wondering, when Deva was explaining where, those kind of things will be like important. But yeah, so that's good to, see that you already have something.
There are a few options to document the way the best way to distribute processes on the various CPU cores. For instance, if you just run 8 processes per node, but each process has 8 threads, then you want to place each process on a different chiplet, and each threads runs the binary threads run on the same die.
Yeah, we have the examples coming in, like more job script coming into that one.
We have some illustration, right?
Yeah, with all the images and everything, so where you can understand much clearer. So with the shared node access, you will be charged only for the partial node usage, whatever you are asking for. So important directive is already I mentioned this one because there is this animation to the buckets.
Isn't that the default happening to the distribution block?
No, I think it's recommended. Like,
okay.
Yeah, because if the other jobs are running in an odd way, like, if someone is asking for 5 cores and the Slurm will try to put it on the 6th core,
yeah,
and then it goes around. So, but if you specify this directive, it won't look into the first CCD, but it will go to the next CCD and try to start from
what is available because you're sharing the node with other processes, so you cannot always obtain your own configuration unless you have exclusive access to that.
Yeah. So, like you said, the main slowdown will probably come in that case because of sharing of the network and other sources.
The memory bandwidth, like, how it's pulling the memory from the.
On the other end of Magnus, you have to come up with a way of using all the resources, otherwise you'll be charged for all the whole node, right?
Yeah.
So this will allow people running single or few just small cores to be charged fairly for what they're using.
Yeah, you can also specify this end task per socket directive. That means socket is basically a CPU. So there are 2 CPUs on each node. Don't get confused with the CPU and cores. There are 2 CPUs and each CPU has got 64 cores. So this CPU is in terms of Slurm concept, it's called a socket. So their end task per socket is 64, or like you can specify 64 or cores or less. If you specify 65, it's not possible. Like, you won't be able to get it. So always try to request our users to use the processors or threads in multiples of 8, because otherwise the next user who is coming into the pool on the same node will be affected if we don't specify the distribution. So another one, probably you might have seen this, not exclusive, it's by default on Magnus. This is exclusive node access. So sometimes I want the entire node. I want all the node for all the resources on this node for my job alone. So then you'll see the more of a predictable performance in this scenario. So you'll get the same performance, likely each time. But whereas with the shared, it depends on the placement and how the resources and different factors that will affect. But with this minus exclusive, you will be charged for the entire node.
Sure.
Even recently, I'm trying to come up with examples like which I'm helping with other user. The user specified minus end task equal to 128, which is good, 1 task per node 128. with this minus minus exclusive, that means I want the entire node. And then after this one, the user specify my hash batch minus minus nodes equal to 32. So
Okay.
all the 32 nodes are exclusively allocated to the user.
Because of the minus minus
Exclusive.
Oh.
Yeah, that last next directive, the user has placed hash batch minus minus nodes equal to 32.
Yeah.
Even though this end task equal to 256,
Yeah.
128 and
Yeah.
1,
Yeah.
because of this minus minus. But the slurm, the user has been using only what is requested here, like 256 stars. So all the nodes. Yeah, I raised the usage was basically the CPU efficiency. I looked at it was 1.5%.
Okay.
So basically the 30 nodes is basically idle throughout the job time. So you should be extremely careful, like, what we are asking. So exclusive is basically requesting the entire node.
Yeah.
So even though if you specify end task equal to 1, and if you specify minus minus exclusive, this doesn't matter. So you will be requested the entire node of that one.
Yeah. So that is only relevant if you are going to use the entire memory and all the codes.
All the codes. Yeah, sometimes of your workflow, it depends. Like, some users memory bandwidth code. So they don't want to launch 128 processors, but they want to launch only 64 processors, but they want to use the more memory. So that means 1.79 times of that to, like, they want more memory. So you need to come across what is the ideal one. So here you might have seen this minus C is all the time coming here. So by default, Slurm currently, it will try to pass these values to the srun command. Again, try to repeat the same thing. With the sbatch directives, you're requesting the resources. Srun is basically using those resources. Sbatch is to request, srun is to utilize these resources. So Slurm will automatically pass this minus minus entars, but no, these are no need to pass it. But unfortunately, there is currently a requirement mandatory that minus C is mandatory. You need to pass it. Otherwise, you might see a difference in behavior. Only the minus C is needed. Other things are all passed to the srun command. So some of the tips for the thing, it's always important to specify all the directives, needed for the jobs, and Slurm will do the maths to specify how many nodes you're asking for. Yeah, right. And the first time you knew a batch script, so try to perform a test run to make sure that it is running correctly and the directives are correct, rather than submitting it for 24 hours on 1,000 nodes. Make sure are you requesting the correct resources correctly or not. Yes, Bradley.
I just had a question about that srun-c option being, you said, mandatory. I've never used that and never had any problem with srun. So there must be some default that it's using and being applied, or it's...
Okay, so maybe, you can try to see with -c and see how the behavior goes around. Maybe a new Slurm version might have fixed it. But there was a communication back in November 2022 or October 2022, where we have requested the users to specify -c directive. Maybe then since then we have updated the Slurm.
Yeah, because one of the Slurm versions introduced this change such that what you specify in the first comment in the CPUs per task will not be inherited by the srun. That was something particular that came out with the Slurm newest Slurm version, so we had to specify the -c, but we can, you can test with and without and see whether you're actually running all the threads. Well, what happens is you create threads, but then you don't have enough cores available to run those threads.
Right.
One thing is, depending on how you submit the job as well. In interactive sessions, you may be using all the cores, but when you do the sbatch, then you may running actually on each process on a single CPU instead of multiple CPUs per process. But
Right.
Yeah, we can, we'll take another look just to
Yeah,
be
we'll
sure,
look into
but
that. Yeah,
Yeah.
because this was the communication back on 9th of November. So when David is our technical manager who sends these messages. So he has specified use minus C, yeah, on the S1 command. So that's what we have been encouraging, but we have updated the Slurm over the years, so maybe things
Right.
might have changed. So we'll look into that.
It may actually be the fact that the jobs that I'm thinking of that do this either use just OpenMP or just MPI, but not both. And so
yeah, so this will come up if you're using multi-threading within a single process.
Yeah, I think this is more important for OpenMP and hybrid.
Because by default, each MPI task will get one CPU.
Yeah.
One CPU core. But if you only use MPI, then each MPI task or process will be a sequential thread, one thread. That's why you use one course. But if you have multiple threads for each process, then that's where you start seeing the difference.
Yeah, okay. Yeah, that's right. So I missed that particular point. Important one. So if it is CPUs per task equal to 1, there is no danger of without specifying -C in the S1 command. But if the CPUs per task directive is set to more than 1, then you can see the difference if you don't specify -C.
Okay.
Placement goes wrong.
And how does that interact with sort of, the good old, export OMP num threads environment command? Does that interact with that at all?
The problem is that, so the -C does not create thread. -C allocates CPUs for the process. Then the OpenMP directive will tell OpenMP to create a number of threads. But if you only request one CPU core, then all these threads will interleave.
Oh, I see. Okay.
Yeah.
Right. Okay. That's interesting.
Yeah. Yeah. Okay, so for the executing the programs, as I said, the first part is shebang line, then the directives is to request the resources, and then SRun part is the way where you utilize those resources, what have been assigned to the job. So SRun is the one. So I just mentioned for -C is mandatory. Mandatory should not be the word. Yesterday I added this one, while threaded running, yeah, threaded or OpenMP programs or hybrid MPI OpenMP programs while running. Okay. So if you want to specify like MPMD, like multiple programs, multiple data, so you want to specify different things, you can request multiple resources and you can use this command called -exact. I said, I don't want to use all the resources that have been allocated for this job, but again, I want to use a subset of the, so you can specify with the command called -exact. And there are shortcuts available like -n stands for minus nodes and all those things. So, and if you're running a serial program, there is no need to run srun command. No need to run because it's a serial, it runs on a sync. But if you use it, it doesn't make any much bad thing, but it's a good to always have a srun command. It's not. So some of the examples we'll see now. So here I'm going to run an MPI program with exclusive access. Here, Bradley, you might have noticed I'm not specifying -C because this is a pure MPI code. So no need to specify -C with S1 command. Here I'm asking for 256 tasks with 128 tasks per node. Currently, there is a Slurm bug. If you specify more than 66 CentOS per node, either you need to allocate relevant memory for the node, otherwise you have to use the exclusive. How can I mention that one? So you cannot say, I want 67 tasks, but without specifying, like 67 means it's not exclusive, like, you are using the partial node.
Yes, yes.
But currently the Slurm will say, oh, that is not possible. Then you have to say 67 times. I can quickly run through it. It's important. So probably, okay, I'll take it up. So I'm just running an interactive session, debug -n task equal to 67. And I'm specifying nodes. Okay, I want all the 67 on the, I'm asking for 6. it says requested node configuration is not available. Why? Because if I can try 66, it's working, like it's going to allocate resource, but 67 is some issue. So what you can do is, we'll do the math. Is it the calculator is visible enough for everyone? So we know 230 gigs per node, each like 230 gigs of RAM per node. So in terms of the megabytes, so 1024 is set 235 times 25. So it is divided equally across 128 cores per node. So roughly each one is getting 1840 megabytes MB of memory. Okay. Now, when I tried to run with the Slurm 67, it didn't allow me. But if I specify, I'm time multiplied by 67. So say, suppose if I'm going back and 123 to 18, 123, there is a because of the Slurm example. Okay. Now it is starting allocating that node. Otherwise, you have to ask for the entire node. So just this is the only more than 66 tasks, then you have to specify. Like if you don't want the entire node in exclusive access, but you want more than 67 cores to 128, then you need to specify. So you can see this one because the job is running. I can confirm it that I got only 67 cores. Yeah, so billing is for 60. Yeah, 134 is divided by 67. So yeah, exactly got that one. So now if I add 281, what will happen? How many cores will I get? Even if I add 1 megabyte more, because I did the exact calculation, you will be getting 68. That means, okay. Yeah, so sure. Yeah, that's the thing. Does it make sense? Like, otherwise, exclusive is to ask for the entire node. So here in this particular example, we are asking for the entire node.
So basically anything more than 66, in this case, it's better not to use exclusive.
Exclusive, unless and until you need all the 128. So if you need 128, then please easily go with exclusive. But if you say I want between, that one, then you have to do the memory calculation as I suggested. So does it make sense, online participants like Vijay? Okay. So here when we ran that, this is the for representation, we are showing only one node here. There are 2 CPUs per node. So 64 on this one and 64, this particular one. So all the processors are equally distributed. So now coming to an OpenMP with exclusive access. So here I'm launching because OpenMP runs on a single node. So you cannot go beyond a node. So here I'm launching one task and with 128 CPUs per task. And this 128 CPUs per task should match the OMP num threads. And this OMP num thread should match the -C here. So there are 3 things that should match here. So CPUs per task, OMP num threads should be equal to the same to the CPUs per task and -C 128. So they all the same values. So the CPUs per task is basically the number of threads per process we are running. There are other 2 variables when important while running OpenMP, which is the OMP proc bind, which is stands for cores. Proc bind is close. That means you want to pack them close to each one, like rather than spreading them throughout the node. And the other one is the OMP places equal to cores, and the other values are socket and threads. So that means you want to place these threads on each of this core. Okay. Yeah, you can see the much of the documentation. It's more explicit. I haven't never come across that code, OpenMP code, that scales up to 128 CPUs per task. Just for example, we are showing. Don't please comment the other way around. So just for the example, but because OpenMP does make an improvement within a single NUMA node. Or within a single socket, but not beyond a socket. Like, that means you're going across. Yeah, if for rare reasons, like, it depends on how the programming, but I haven't come across. So preferably what I can see is try, like for OpenMP, whenever you do a scaling, try with 1 means serial. So try with 2 threads, which are placed next to next, and then go to 4, then 8, then 16, then 32, then 64, and then 128. 128, if you come across a thing, but maybe you can drop me an email, then I can, I think one of the best code I can say. Yeah, normally they don't get that much of going across the
it's hard to get good scalability in the sense because you have so many cores and there are so many memory regions that it starts to
exactly, and going beyond. So you can see this this particular one box is the CPU, one CPU, another CPU. So that means you're jumping across the.
On Magnus, you had less cores, 24 cores,
24,
all sharing the same cache. So the performance was better in terms of scalability.
People have got up to 24.
Relatively scalability. But in this case, you have to be more careful around to use all the resources.
Yeah, going up to 128 is quite ambitious.
So you will at the most get 32, is it? With the way the layout is.
No, 2, 8, 4, 8. You can go in and
sure. I think
every time the benchmarking on multiples of 2.
Right.
So when you do the OpenMP.
Yeah, but in general, if you go past 16, then you see that the efficiency start to drop because depending on the way you organize your code, you have to organize your code properly such that threads that are on the single GCD do the most of the reduction. Then you can do at a higher level reductions across those GCDs or like chips. So you organize the computation not as a flat parallel computation, like to try to go to 128 cores to reduce the result to 1, but you just go from each group of 8 threads, compute a partial result, and then you go back up a level. So it's more hierarchical to make sure to make good use of those caches. But it's more complicated to get.
So it's all. So another one is the hybrid MPI OpenMP example. So where we are using both MPI and OpenMP. So for each process, you're trying to provide more CPUs per task. So here in this example, I'm running 4 tasks, but only 2 tasks per node. So that means the first process goes here, and the second one goes, and the third one goes to the second node, like that. And the CPUs per task. So for each task, we are providing 64 threads. So here in this case, in the pictorial, the first process, the 64 threads are sitting on the same CPU. But of course, here in this case, like we mentioned about the minus distribution equal to block, it's a good practice, but in this example, we have not specified, we should have done it. So this is the thing, like, when you specify here, because since it is a hybrid code, -C64 is needed, like, the value should always match. Because important one is how many CPUs per task we're requesting. That should match with the OMP num threads, and that should be matching with the -C flag. So they're all the same. And in shared access, by default, it's a shared mode. Now I don't want to run the entire node. You can see there is no -- exclusive flag here, but you can specify, 64 tasks per node and 64 tasks per socket. That means socket is 1 CPU. So, and you can specify block. Here in this case, this one is an optional one because you're asking all the cores on socket. So it's by default, you're doing the same thing already. But if you're specifying maybe 68 or something, then the block does make a difference. Again, here, -C1 is optional because it's a pure MPI code, but it's not going to hurt if you specify it. This is a shared access. You can see there is no -- exclusive. If we specify -- exclusive, this one is also allocated, but you're not using. You will be charged for it. So again, always remember, try to use multiples of 8 MPI process for best L3 cache. So each CCD, the purple thing in between is just the L3 cache, which is shared across the 8 cores per CCD. So memory request. So another example, if you say, I want only 1 task, but I want more memory. So here in this case, you can specify with the -- mem flag equal to 58. So 230 is equally divided among 50. So 58 gigs means how many threads will come? Like You can able to specify at the moment from this picture, I can see 32. But you can you can confirm it. Like, if I say 58 times 1024 in terms of RAM, and each core is getting 1840 MB. So 32.27. So this is not exactly correct. So 58 means you're basically getting 33 cores. So this one is 30. Yeah, okay. This is another mistake which we need to rectify. So you'll be given 33 cores. So basically this one should be 57. Maybe I'll just do the
the concept. We got the concept.
Yeah, okay. Does it make sense? Like, because if you specify 58, it will go 33 cores.
Right. It's the same thing I discussed in the accounting section. Yeah.
So maybe I'll just to avoid anything. And requesting a GPU. Okay, sorry, I moved something and the directive has changed. So this one should be on the crest. So if you want to request a GPU, then you need to specify the minus crest GPU and how many GPUs you want to request per that node. And important thing, as Christian mentioned, for the GPU requesting, you need to specify project ID minus GPU. The suffix minus GPU is okay. So there are two different accounts, one for the CPU, one for the GPU. Each GPUs have got 8. Even though you requested only one task, by default, you will get 8 cores. Yesterday, we mentioned that there are 64 cores on each GPU node and with 8 GPUs. For the proper placement, if someone requesting one task, you'll automatically given 8 cores that is associated with that particular CCD. Okay, the CCD has got 8 cores, so that each CCD is attached to a particular GPU. So that particular entire CCD will be allocated. Even though you said, oh, I requested only one CPU. No, because for the proper placement, you will be allocated all the 8 cores on that particular CCD. So that when the next request comes, it will be properly allocated from the next CCD. Okay, otherwise, people will get affected. Yes. And the other one is here is an exercise. It's quite simple. So please go through that one through the training modules.
We have 30 minutes till the end of the training session. So we have 30 minutes left, just as a reminder.
Okay. Okay, in this one, we have seen about quite a number of process and everything, how to submit jobs and syntax basics of different jobs. Important thing is -L for the shebang line to have a fully configured batch script, and always try to have a test your job script before you run it. Like, it's always important. Going to the it's 11:30.
Yeah, that's what I'm telling you.
Oh, yeah, sorry. Yeah.
So how many you have remaining?
Is it okay? I think we went a bit up slower.
That's okay.
I'll try to make it this one as a short one. Is it okay, Christian?
Yeah.
Okay, yeah, okay. You should have wanted me. I think I'm a bit slower because when I was mentioning the examples and everything. Any questions online, participants? Okay. So quickly do this one because we now created a job script now of batch script. Now testing the job run. So we basically try to, before you run the job, why should I test the job? Because make sure the scheduler commands and the program configuration which you're running is correct and as needed. And you're not asking for more resources than what is needed. Like, appropriate wall time, you're asking how many CPUs and nodes and CPUs you're asking correctly. And also, as Bradley mentioned for the comment, like, if someone is submitting merit allocation, you need to have this testing the job runs, make sure that you can provide a proper plots to make sure, okay, it's I requested these resources, it is doing this one. So I think always use the debug partition if you want to do some testing rather than going into the default partition. So first time when you're going to submit a job, make sure the directives are all correct. Okay, so it is asking what it is needed for. Always, like, when you're trying to test a job, do not try to test it on a large scale workflow. So try to find a smaller problem size, a reasonable problem, which is a representative of a typical problem, and try to execute it and see whether is it doing what it is supposed to do it. Okay, what it is supposed intended to do, that's okay. And the second one is to optimize the resources. So as I mentioned, if you underestimate the wall time, your job will be crashed off way, and overestimate means your job will be waiting in the queue for longer. So always run a problem size, a fraction of your problem, and try to see, okay, how long does it take? And then extrapolate and try to see, okay, for my real problem, this much time is likely to take. And maybe when you're running for the first time, it's okay to run for 24 hours and try to see, okay, for this problem size, I requested 24 hours, but it completed in 12 hours. And you can, next time you can change your wall time accordingly rather than going for the default one. Yeah, so memory requirements, if you don't specify, your job will crash. Like you will get this out of memory errors and everything. So you need to request memory and the resources correctly as needed. For MPI scaling tests, if you're doing a scaling test, try to start from 8 tasks per one node and then go to 16, 32, 64, and 128. With MPI, you can go multi-node. So once you reach 128, you can go not at maybe not at the one, not 192, better to go at the scale of like always going multiples of 2. Like, now after 128, you can go at 256. 512 is 4 nodes and try to see how it is scaling. Sometimes the scaling behavior will stop halfway through that for MPI programs. Not all the MPI codes, based on the problem size, it might not reach the scaling. For OpenMP applications, you can only do on a single node. So start with 2, 4, 8, 16, 32, 64, and 128 core CPUs per task, and try to see how your OpenMP application is scaling. As I mentioned, like, in our experience, we haven't seen up to 32 is okay, or even 16, the max of 16. So then rather than asking exclusive for all the 128, you can go up to 16. Here is an example of a LAMP's molecular dynamics code, which is a popular one. Maybe 20 to 25% of our users run this code. This one is on a Magnus system, which has got 24 processes. You can able to see how the scaling. So when you increase the process, how it is scaling over the number. So you can see after a certain point, it already flattened. So there is no point of going up to 3000. Yeah. You can find the sweet spot. Okay, what is the right number where my code can get the best out of it, like rather than going all the way. So there are two important metrics. So parallelism comes at a cost, like that is more important. So you need to make a balance. Do I need to go really faster, or you need to also take into the cost into consideration? Sometimes it might run super fast, but the cost is also too high. You need to see what is the right balance. So here in this case, maybe around this high point, you can basically stop, like, then after that, it basically flattened. So two important scaling metrics, which is the weak scaling and strong scaling. And strong scaling. In weak scaling, what you basically do is you keep on increasing the problem. So you keep for each core, you keep the same amount of workload when you're increasing the number of cores. Weak scaling is easy to achieve, but whereas strong scaling is harder to achieve. That means you are not increasing the problems, but you are just increasing the core count. That means each core is trying to get more, like as you go up with more number of cores, you're getting less problem, like less size for each core. That means not enough work for the cores to get. So the strong scaling is harder to achieve. And also there are two metrics, important ones, important when we are submitting an allocation application. Speed up. What is the speed up to my reference run? So how it is scaling? Is it improving? So you can see the ideal speed up here in this graph. So this is what ideal I want it. But in reality, it is going this way. So you can weigh maybe around this point, you can say, okay, reasonably to stop. Yeah. Because rather than this one is running faster, but you're not getting this, the cost is also higher. Okay. Now, summary, basically always test your jobs. Make sure what you're requesting is correct, not like the user who submitted recently 32 nodes. wasting 30 resources. So yeah, I'm not pointing any user, it happens.
Yes.
So a small one directive, one mistake with this user at the end of the directives, minus end nodes equal to 32. Out of nowhere, user added.
This is especially true because on Garavala you were not charged for it.
Yes, I think that's
it's a good warning for that because now be careful on especially if you have your own marital location, that's where you'll be charged, and you need to be careful on that. In general, it's a good practice to just use the resource you not to let the resource go to waste. Even on your partition, you will also may block other people to run jobs, Okay, just
So I take it too long. Yeah, I didn't expect. Yeah.
Okay. Okay, the last part is I'll go the many slides, but I'll go on high level on the most important parts because we have 20 minutes left. It's about managing project data. So it means that you produce data or you reading in data to process. You work with data and how can you have this data saved in the long term? Given that Scratch is not a place to save data, then Pawsey, what Pawsey provides is Acacia and object storage. What is an object storage? Essentially, it's a system designed to store large volumes of data in the petabyte scale. Pawsey provides 60 petabytes in Acacia, but it's been, I don't know, it's already been upgraded, but it's scheduled for upgraded to up to 130 petabytes. And there's been talks about it. And
probably some of them
providing
groups have got around 500 terabytes.
Providing that type of scale storage is not really possible with a traditional file system, or would be extremely expensive to do so, because traditional file systems have a more complex layout. So what is a file system? Traditional file system has a hierarchical structure. You have data, could be bytes or characters, are written into a file. They're organized in files, and the files in turns can be organized in directories. This is how you organize your data on disks. So data on disks are written as sequence of bytes, in blocks of bytes, but then these are presented to users as organized in files, and these files are organized in directories. So it's a rather complex structure, and a file itself can be read, written, modified. So a file is not like an atomic unit. You can open it, you can go to a certain position, modify that position, save it, and go back. So you have quite a lot of flexibility, but that will comes at an expense in the software to manage all that complexity, and then the resource required to support the structure. So the unit of data in the traditional file system is actually the byte. So you can the granularity you can modify the file is in the byte level. However, the object storage, to scale at the level it can scale, it gives up that flexibility. So in the object storage, it's the single unit is what is called an object. So you can associate an object is basically a blob of data. You can see it as a file, but a file we cannot call it a file because a file you can modify, you can open it, you can navigate through a file, but an object itself is a unit, it's just, and you can only read it, you can only copy it, move it, you can only store it or retrieve it from this object storage. Well, inside the object storage, inside Acacia, this object is immutable. It's there. You can only retrieve it or place it there. And an object storage is also a flat structure. There is not a hierarchy. It's basically you have this, imagine this object storage like a giant cabinet or a giant like place, and then you have buckets as only way to organize these objects. So it's a one level structure. We have only buckets to organize objects. So you can have a bucket for a type of objects, another bucket for another class of objects, but then you cannot have buckets within buckets, like you can have directories within directories. So you can only have these buckets, and then you place objects in the buckets. So that's the main difference with the file system. Because you have these flat structures and you cannot navigate or open modify objects, then the requirements to support this type of structure is way less demanding, and it's cheaper. It's cheaper to deploy. Because the software to manage this is not as complex as a file system. So you can spend more money on the actual hardware to store data, and also the software itself can scale better because it does not have to do all the complex stuff the file system does. So that's the main difference. Okay, so essentially what's happening here is that we have a large capacity object storage, and you can use this object storage is accessible by any other computer at Pawsey, so you can access from Cetonix, but from Nimbus or Caravana, but Caravana is going away. But you can also share these buckets or access to object storage to other people external to Pawsey if you provide them with a link. So it's a good way to store data, project data, also to share them with other people. Yeah, we have here a representation where we see that Acacia, the central system, can receive data from the Scratch. You can move the data back and forth from Scratch, but also from the data can be downloaded from other institutions if provided access. So setting up your Acacia. So when you ask for allocation of Cetonix, you will be provided with a certain amount of Acacia storage, but you will need to go to this specific interface to set up access to Acacia. Set up access means that you need to create your credentials, which turns out to be a pair of access and secret key. Without going too much into details, essentially you go on the portal. You have in your origin portal, then you have the tab Acacia, manage keys, and you can generate your key. I mean, this interface is very useful because it will also gives you the exact line you need to copy on Cetonix so that you can configure your access to Acacia from Cetonix or from your laptop. Then what happens is that once you configure your access, I'm going just quickly through that. The credentials will be stored in your home directory that is private to you, so nobody else can access it, and you should not share your access credentials with other people. How do you use Acacia? You need a specific program to communicate with this storage system. So it's not like you can write on Scratch using the interface to a file system is basically a system calls read, write, this file, open this. But to communicate with Acacia, you need to interact with an external system, which through a protocol which is called S3. It's a web-based protocol, and you will need a specific client, a program that reads or writes objects into the from and to the Acacia system. That's what's an S3 client. So we suggest rclone, which is installed on Cetonix, and you can use rclone to interact with Acacia. And you can, when you set up your keys, you can specify rclone as your default tool of choice, and the interface will give you the command line to set up rclone on the system. You can also use this. If you have a Python script, you can also actually use the Spoto library that allows you to read and write objects from within a Python script. That's I never use it personally, but it should allow you to read and write objects directly into your process memory without having to write a file on the file system. Okay, now this is basically a few slides showing how to configure access with rclone. I will go rather quickly through this because most of you should have already maybe tried to access this. But as I said, the interface, when you generate the keys, it will give you the exact command line you have to do to set up everything. So what happens is that it will create for you this configuration file where you store your keys. It will look like something like this one. will ask you what type of HSKD endpoint is the Pawsey endpoint, and etc. But how we are going to use this once we configure we have configured it on Cetonix. We have a few commands you can run. So first of all, if you want to store an object on Acacia, you will need to create buckets because the objects belong to a bucket, and we will have to store on the Acacia. We will have to place them on a particular bucket. Initially, there are no buckets. You will need to create. You will need to create a bucket. Now, what is this remote name? Essentially, it's your account on Acacia. So you will have a personal account for yourself, and you will have an account for your projects, for each of your projects. So this remote name might be MWA VCS because it's the Acacia account for the MWA VCS group. And then you can create a bucket name. The name has to be unique across all Acacia. So for instance, if you try to create a bucket name test, it will fail because it says there is another bucket named that way. So a proper way to name the bucket might be following a convention such as your username and then the name you want to give the bucket. You can list the buckets on the system, and you can list objects in your bucket, similar in a way you can ls a directory. One thing that, so what's an object in this context? How you transfer files, how files become objects? Usually, well, there is this easily the easiest way to consider this, to see this, is that a file can become an object. So the file, it is a mutable object. Once you move it to Acacia, it becomes an object, and you cannot modify it there. It becomes a unit, and then you have to move it back on the file system, and then it becomes again a file. Let's see if we have some examples. So this is a few examples here. So we are creating a new bucket. For this is your account. We create this new bucket here. We see that we created. This is the content of our account. So we have this bucket which is nicknamed and --Pawsey project. Okay. What happens there? Oh, it's because there is no such bucket. So what happens? The copy single files as object, as I was saying. You can copy the file and that becomes an object. But the problem is when you have many files, that can become cumbersome and also hard to organize because you cannot have in theory, you cannot have multiple packets, one under the other. So one easy way is to tar files that are together, that that are semantically part of a unit. You use them together, so you just tar them together and you transfer them as a single object to the store, and then you untar when you take them back. But what happens is, because people are so used to the file system way of organizing data, so files and directories, one can mimic the organization of a file system, so hierarchies, using a specific convention in the file name. So you can flatten the structure of a directory by taking the whole paths and make them the file name of the object name, right? You can do that using this clone sync. So if you use this command, you can synchronize a directory tree to your Acacia account, or within a bucket of your Acacia account, but what will be copied is not the directory structure. It will be kind of mimicked by naming each file with its full path in this tree.
Okay.
When you copy it back, then the clone takes care of reconstructed the file system hierarchy based on this name. This is all well documented. Okay, so
either tar or untar or just use clone sync.
it really depends on the type of data you have. For instance, if you take, for instance, a VCS observation, you can think if you use voltage data for your storage voltage data. I think that would be nice. You have a bucket, which is the observation ID. And then the DAT files, there is no hierarchy, there is just a bunch of DAT files. That's easy to copy each file as an object. And when you use a clone, you can actually use multiple cores and you will do this copy in parallel. It's very fast. If you do this copy in parallel using the copy partition, which is another suggestion we have, then this copy is very fast. And there is no point in tarring or untarring that because you have just more time. But if you have lots of smaller files, like documents or things that you don't really access that often, you can tar them. It's just easier to manage. Yes, Bradley?
I just want to note that for a 4800 second VCS observation, that's about 120,000 files. So actually that wouldn't fit in the Acacia bucket, just as a FYI.
Oh yeah, sure. There is in fact a limit there.
So that we don't do, right? We only do like process the files.
Probably in that case, you would have a mid strategy where you just tar in groups in the case, but that adds computation because you're doing compression, decompression. Or you can create multiple buckets.
I was just going to say, there's basically never any reason that we should be putting raw voltages on Acacia anyway, since they exist on Bankshare and are accessible via ASVO. So it's a bit of an extreme situation to be talking about, but
Thanks for I was just the first example I had in my mind, but it's definitely it's already there. You just download them and then use them. Then maybe you store visibilities or whatever.
Exactly.
These intermediate steps, files that you were talking about that you need.
For us, one of the big things will be like the FITS files of the beams. Because the process of generating them is very high, and that's also like an important data product. We want to make the public to be accessible.
Cool. Thanks, Bradley. And the Arclon sync may be, but if you have, it really depends on the project. I think if you have a measurement set, it would be good to tar it, but if you're using frequently, maybe I'm not sure whether ArcSync could work there. Okay, then you have a few commands to copy back and forth data. You have this Arclon copy source target option, so you can copy you can copy files, objects using this command. Delete objects, but also I think we have an example here. You can copy entire directories as well, like in this way, like using Arclon copy. So you copy the entire content here in this that is stored in originals. Any questions so far? Okay. Since we are almost towards the end, I want to see whether there is something I need to say. Okay. So one thing to say before I forget to say, I don't know whether it's in the slides. When you do Arclon using Arclon as a client, when you copy on Scratch, by default, what will be saved there is the modified date will be the one that was initially stored on Acacia. So you need to be careful to update those states such that the push policy won't cancel your data that you just copied. Although, yeah, and so you need to update. There is a special flag in our clone such that you can update this modified data or to the date you copied back the data on Scratch. Also, as I said, you can move data using the copy partition and submit jobs using multiple threads and multiple cores, so that our clone can make use of the multiple parallel transfers and you get your data faster on the file system. For instance, you could include in your workflow at each stage. Yeah, Stefan. Yes, Stefan.
Yeah. So for specifying resources for a copy job, particularly if you're just using rclone to grab objects, is there any real variation to how much resource is required when you're rcloning? Like, does an object have like a size or anything like that needs to be taken into account when rcloning? Like, certain copying jobs, sometimes you need a large memory at the end to with rsync, for instance, sometimes requires a certain memory amount to get the thing over the line. Does rclone have a similar limitation?
Not that I know, but I'm not like a large user. What do you think, Eva?
Yeah, we haven't. Yeah, mostly.
So what I know is that the more cores you give, then it's faster. The transfer is faster. So our clone should also be able to do progressive transfers as well. So that if
it stops at one point. I know rsync does it, but I'm not sure about our clone.
I don't know of any limitation in that sense.
Yeah, maybe if you're starting for the first time, based on the size, you can see like request the entire copy partition, maybe full, maybe a reasonable number.
But I don't think,
and then reduce it accordingly.
I think it will be, it should be writing it like stage on the file system, so you don't have to have the whole file in memory by the time you finish transferring everything. But I'm not 100% sure about that.
Yeah, I mean, I've never noticed an issue with that, but it just in terms of
what we suggest is using multiple cores because it just can transfer more objects, so could be faster at transferring the files.
Yeah.
Okay. So what we suggest here essentially, if your main computation depends on having this data transfer from Acacia, you can use the slam dependency function such that you can specify that the dependency of the main job is another job. It depends on another job that is the job transferring the files back from Acacia to the file system. So you say, don't start my computation job until the data are completely transferred. So the other transfer job is completed, and you can do that with this sequence of commands. You can get the ID, the job ID of the computation, the job ID of the data transfer job, and then you can specify it as a dependency. So the job as the computational job as a dependency on the other copy job to finish transfer the data before starting. A few exercises. So in this case, the workflow essentially says that the copy is running, but the job on the work partition that is supposed to use the data copied from the partition is waiting because depends on the other one to finish. So this is a way you could introduce Acacia in your workflow. You can also create links to objects and buckets, so you can actually share what you stored on Acacia to other people.
Mm-hmm.
It provides a web link that people can actually use to download data from Acacia, from an external host. And this is an example.
And can you just download that with like wget or something? Or do you have to use rclone?
No, you can use it. It's a web link, so you can use any any
Oh, cool.
any HTTP,
Okay.
HTTP.
That's fantastic.
So wget.
Yeah, because I mean, I can talk to you separately, but Bradley had suggested that this could be a possible way we may be able to share our data products
Yes.
with our smart data release.
Okay. So well, this is the summary. We went really quick through artificial intelligence.
Yeah, I went too long.
So we have
been using. Most people are using it.
Yeah, so I know people use, so should be comfortable with this. But what my I-level suggests is that you can actually include this in your workflow and using parallel transfer, the copy partition. If you orchestrate it well, it should not be a pain to stage this data automatically on Acacia without you thinking. If you set up a system such that it backs up every stage of your computation to Acacia, depending on the size of the transfers granted, you should be less impacted by the scratch push policy. If after every stage you can store automatically on Acacia, depending on the data you have to store, of course. There is a bit of a learning curve, but once you set up a system to do that, then it should be helping you quite a lot. Yeah, and that brings to the end of the presentation and the training. So if you have any questions, please speak now. Any final comments or remarks if you have any questions overall that have not been answered so far?
This is the first time I have done a proper training. Even though I have been a user, I found it to be like very comprehensive, starting from like very basics at the start. Partly maybe because I was here and listening. So lots of things, bits and pieces we pick up from people when their discussion and things like that. Yeah, that's great.
There's
Bradley kept reminding me every once in a while that there is a extensive documentation. Maybe I should start like now I know what all is possible.
Yes, Bradley.
I just want to make sure that the slides and stuff will be shared or made available at some level. Just having those, or even.
The slides, yes. So what we are doing, we are going through a process of reviewing them, updating them.
Yeah.
And they should. The previous versions should be available on our documentation.
Yeah, it's on the document.
If you look for training material, it's there in the documentation.
I see.
Devo, would you stop the recording or?
I'm still going.
Okay.
You want me to stop?
Oh, well, we can keep it and then.
Okay.
Okay. So slides will be made available, especially the updated ones. We are going through the process of updating them. Next week we will have interns coming at Pawsey and we will run a similar process as well for them.
Okay, cool.
The summer interns.
Summer interns at Pawsey.
But for them, it will be a more basic version.
No, for them it will be done over multiple days.
Okay. But do you cover everything for them?
Yes.
Okay.
So yesterday Victor has shared that one information. So probably if you see that, I'll post that again here in the chat.
Any more questions?
Probably was shared. I just didn't actually register to attend, so probably.
Yeah, that's right. Okay, yeah.
Okay, if there are no more questions, then we can call it at an end. Thank you for coming and hopefully, start using Cetonics. And if you have any questions, submit tickets and we'll try to answer to those.
MWA migration is the main priority for our team at the moment. So if you need any assistance,
I'm working full time on that.
Yeah, Christian is there, and then help ticket is also so that we can keep track of what is happening. We are ready to help. Okay, thank you everyone.
Thank you both of you. I think it was very useful.
And now
Recording. I went like I clicked stop recording.
Okay, stop.
Oh, the problem was it